It seems that humanity has gone a long way since the first people appeared on Earth. We've invented so much cool stuff and developed new technologies. We've risen above other species after having built an advanced civilization. We've come from living in caves and cooking our food on fire to walking on the moon and creating 3D breakfasts. Does it mean we can be considered a Type 5 civilization? Oh, I see you're confused. Let me tell you about these civilization types and what they mean. The Type 1 title is given to species that have managed to harness all the available energy of their home planet. That's why this civilization is called a planetary civilization. They gather and store this energy to satisfy the demands of a growing population. We would need to boost our current energy production more than 100,000 times to get to this stage. And then we would be able to get control over all natural forces on the planet, like volcanoes, storms, or earthquakes. It's hard to believe, but it's actually a very basic level. You'll see it later. As for now, let's move to a Type 2 civilization. It can use and store energy at the scale of a star system. That's why this type is often called a stellar civilization. Experts have suggested several potential ways to do it. The most popular one is called the Dyson Sphere. This hypothetical device could encompass every single inch of a star, gathering its energy and transferring it to the planet. What would so much energy mean for the Type 2? First of all, nothing we know about could wipe out such a developed civilization. Let's say a moon-sized object entered our solar system and was heading towards Earth. No need to panic. We would be able to vaporize it as soon as we noticed it. Or maybe we'd just move our planet out of harm's way. Now, a Type 3 civilization can control energy at the immense scale of the entire host galaxy. That's the reason it's called a galactic civilization. The inhabitants of such a civilization would probably be totally different from the human race. They could be cyborgs, both biological and robotic beings. Maybe there would be colonies of robots capable of self-replication. They would spread across the galaxy, colonizing star systems. And still, these species would be restrained by the laws of physics, unless they figured out how to travel at the speed of light. At first, the scale describing civilization types didn't go beyond Type 3, but later, it was extended, and that's how Types 4 and 5 appeared. A Type 4 civilization knows how to harness energy at the scale of the universe it lives in. This could probably allow its inhabitants to live inside supermassive black holes. In any case, they would need to tap into energy sources we can't even imagine at the moment, using currently unknown laws of physics. And finally, an incredibly advanced Type 5 civilization might be living somewhere out there. If we reached this level, we would be able to manipulate energy both within our universe and other universes. Of course, at the moment, we're a very long way from achieving a Type 5 civilization, but it's not impossible. Assuming our world remains intact, we might continue advancing with every next generation. Then, a day may come when we'd be able to travel anywhere we want in the multiverse. Maybe we'd even use wormholes, theoretical bridges using space-time that creates shortcuts, reducing travel distance and time. We'd be able to tap into mysterious dark matter to produce energy. And we would find the answers to tons of mysteries about us and the universe. But guess what? At the moment, we're not even a Type 1 civilization. Yep, we're not even on the scale yet. Duh! First of all, we're facing some physical limitations of each type of energy source. Plus, we'd need to balance them not to trigger even more climate changes and not make pollution levels rise. Scientists researching this question have concluded that humanity could potentially reach the level of Type 1. But it wouldn't happen until at least 2371.
So how alone are we in our galaxy? Crickets. Yep, we're mostly alone out here. But are there other civilizations lurking somewhere out there in the depths of the Milky Way? Could they possibly have evil intentions and be a threat to us? Hey, like we need more threats. Well, hey, let's have some fun with this. Some theorists reviewed humans' history and past actions toward one another. No miscongeniality awards there. And assuming they were somehow like us, used this to calculate the probability of space invaders. They determined that there could be 4 evil civilizations in our galaxy. The 4 could be eager for intergalactic domination, or maybe just for a good game of dominoes. They could be highly advanced in technology, or they've only just invented an evil version of game consoles. To understand how advanced these cultures could be and what to expect, there is a way to define their threat levels. A method called the Kardashev scale analyzes intergalactic nations' possible abilities. With 3 different levels, it reviews the amount of energy a civilization could take from their star, indicating their tech level. This only includes those that have reached interstellar communication. So any other beings out there using, let's say, space pigeons will of course be excluded. Type 1 shows that they can harness the energy from the sun, but only from what is received within their own planet, like solar power panels. Type 2 is where they can use the energy directly from the sun, like through a Dyson sphere. It's used to harness all of the sun's energy, having been built entirely around it. And lastly, Type 3, where civilization can use all elements provided by the galaxy, with the power to not only harness the energy from stars, but also black holes, even the central supermassive one. These levels are important to assess how advanced civilizations could be out there. The Milky Way is estimated to be around 13.6 billion years old. Modern humans have only been around for the last 200,000 years, and we're only a Type 1. It's scary to imagine the time other beings have had to develop. We're considered a bit of a late bloomer in comparison. Earth is, shall we say, late to the party because we're located on the outer arms of the galaxy. Mathematicians posit that more centralized star systems have had more time to progress. Now, with that in mind, how common would other intelligent beings be in the galaxy? With all the life-ending events Earth has survived, it's a miracle to have a planet like ours, and that we would be unique. Or are we? Well, there are 100 trillion stars in our galaxy, and there are up to 200 billion planets, with an estimated 300,000 exoplanets capable of sustaining the kind of life we know about. From those habitable planets, how could we tell which ones have other beings eager to send us an email? No one's had the time to individually count, of course. The Drake equation can give us some rough numbers if we take averages of a few key factors. It breaks down the criteria of how many planets with life are intelligent enough to make communication. The numbers are huge, considering how many stars might have planets. And from there, we distill it down further to those within the habitable zone in the solar system. This zone is called the Goldilocks zone, as it's not too far from the sun and not too close to it. It's just right. We reduce the numbers even further by calculating which of those habitable planets will then be able to support life. And from those random places, the equation takes the probability of how many intelligent beings will be and if they are intelligent enough to communicate. The criteria is complicated, and so it's not an easy equation to explain. But from its estimate, there could be up to 100 million planets with intelligent civilizations. But just like with Earth's history or struggles, these civilizations may also have their own challenges. World-ending events should be thrown into the equation, like asteroids, solar flares, supervolcanoes, and supernova. They could also destroy themselves through technology, like AI dominance or nanotech, or by affecting their own ecosystems and running out of resources, or by just acting stupidly. If we take these into the equation, the remaining living civilizations could be around 15,000. But what could they possibly want from humans? We do have an abundance of rare Earth materials that could be of value, ready to be harvested and easily collected. Besides an appealing vast amount of water they could suck dry, hydrogen is a required element of rocket fuels. Though these things aren't exactly rare in the galaxy and could be harvested easier from other closer solar systems or asteroids. Our technology might be intriguing to them. Our range of innovations on Earth, invented while being isolated in separate countries, help provide different technology paths around the world. Other civilizations could have followed a completely different route, and didn't learn the importance of many things we have here on Earth, like karaoke. The same goes for applied sciences, where they may have evolved in different atmospheres with different elements. Their science would be mainly affected by that, and ours would provide them with more knowledge. Then, there's one of the rarest things in the galaxy, that Earth can support life. This would be very useful for an intergalactic traveler, rather than going through the long process of terraforming an unlivable planet. Why not just take it? With a cozy outpost, it would be a lovely little holiday destination when they need some time off from conquering other civilizations. Fortunately, they wouldn't be interested in eating us, or probably wouldn't have an appetite for anything on Earth. They would need to have similar biochemistry and require the same enzymes to process the molecules we're built from. Whew! But the most likely thing they would want is to remove any competition. The biggest threat to them is anything that would provide a challenge to their domination. But before you get too frightened by these evil civilizations, this was based on human behavior. It's possible that any beings out there could lack or avoid many of our human emotions. For instance, their capacity for anger might be limited, or they could have evolved without it. They could come from a world with a history so different from ours that they could be overly trusting, making us the bad guys. But again, they may also lack empathy and other positive traits we have. Well, let's hope they only have our nice traits. Luckily, there's a big thing that separates us from everything else. The galaxy is huge, and it takes a very long time to go anywhere, even to our closest solar systems. The fastest thing we've sent into space is the Galileo probe, which travels up to 100,000 miles per hour. Even so, it would take 72,000 years to reach the closest star system, Alpha Centauri. Still, with a newly proposed laser-guided probe that could travel at 1/5 the speed of light, it would yet take up to 20 years to make that journey. On a larger scale, the Milky Way is over 105,700 light-years across. If a civilization was even capable of light speed, it would take them hundreds of thousands of years to travel from one end to the other. With a huge distance between the small number of civilizations, the only successful contact would be through advanced interstellar travel. But to achieve such a long journey, the greater the mass to be accelerated, the more energy is required, so it's not likely anything too large will be sent. But they could travel here very quickly in a small shuttle, using the ability to break cosmic speed laws. They may already be here, watching us closely, or just binge-watching Netflix. They would need very advanced technology, and the number of species obtaining this is theorized to be only 2 out of the 15,000. That means there's a 1/100% chance of evil civilizations capable of visiting us soon. If they do know we're here, and they want something from us, it's likely to take them thousands, if not millions of years to arrive. So, we've got plenty of time to relax.
Did you know that humans are real space people? You were born in space. Heck, even I was born in space. We were all born in space. But for humans to be here on Earth, so many conditions have to be precisely correct that it's highly improbable that we even exist. But we do. First, we, and any other space creatures who might be out there, have to live on a planet orbiting a yellowish-white star, not a red star or a blue star. Not a blue star, because they burn out too quickly. In a few million years, there wouldn't be time for evolution to do its relatively slow magic and produce intelligent beings. Blue stars also tend to swell up and turn red when they collapse and explode. It makes it highly unlikely that any civilization could prosper near a blue star. Red stars which are by far the most numerous kind of stars, don't seem like good prospects for intelligent civilizations to orbit around either. Red stars are so cold and so dim that a planet that could grow a civilization must orbit very closely to the red star, which would expose the planet to intense, deadly X-ray radiation. So, though red stars are the most numerous and appear to have many planets orbiting them, red stars are a no-go for hosting intelligent, civilized life like our own. That leaves the yellowish stars, about 10% of all stars. However, an important fact must be met before considering the possibility of intelligent life living around a yellowish star. That fact is that the yellow star must be a third-generation star. Only third-generation stars will contain sufficient chemical diversity to sustain advanced life forms. Each time a star explodes, heavier, more complicated elements are created. The explosion expelled these elements and eventually found their way into a nebula. Gravity within the nebula will gradually form the next generation of stars, and so on. Our bodies need calcium for our skeletons and teeth. Our brains need zinc to help create the electrochemical signals that make us move, feel, and think. Our blood needs iron. Therefore, our bodies need to have formed around a third-generation star, and a yellow one. Amazingly, Earth has all the different elements in the universe, all 94 naturally occurring ones, from hydrogen to plutonium. Maybe that's why we're here. And we have to thank our third-generation yellow dwarf sun for that. Why yellow? Because yellow stars burn very steadily by nuclear fusion without significantly changing brightness over billions of years. If our sun became just 6% brighter or dimmer, Earth would become too hot or too cold to sustain civilized life. Fortunately, Earth is in the habitable zone around the sun. The habitable zone is where liquid water can exist on a planet. But that brings us to the second condition necessary for intelligent life to live in space: the planet itself. Recent studies with the Kepler telescope have shown that 1/4 of all yellow dwarf stars may contain Earth-like planets in the habitable zone around yellow dwarf stars. That figure is somewhat debatable. It might be as few as 1 out of every 33 yellow dwarf stars, but that's still a lot of planets orbiting yellow stars in habitable zones. So let's consider the second essential component for intelligent life in space: the planet itself. The planet that would bear intelligent civilization must have many particular characteristics that aren't easy to come by individually, and even more rare to find in combination. Most importantly, the planet must have protection against the star it's orbiting. Because stars shine by nuclear fusion in their cores, gas in the outer shell of the sun, called the corona, gets blown off into space in what's called the solar wind. Our United States satellites take constant readings of the force of the solar wind, which is mainly electrified, ionized, hydrogen nuclei, along with a smattering of atomic nuclei from the many other elements found in the sun. It's not the atmosphere that protects Earth, it's the magnetosphere that stops or deflects the dangerous solar wind, causing aurorae when the solar wind is attracted to Earth's magnetic poles and electrifies the air of the upper atmosphere like a fluorescent bulb. Without a magnetosphere surrounding it, any planet, even those in habitable zones, would be toasted by a constant rain of ionized hydrogen nuclei from its star. A planet with life on it must have a magnetosphere strong enough to deflect the solar wind. Not every planet in our solar system has a magnetosphere. The gas giant planets, Jupiter, Saturn, Uranus, and Neptune, have magnetospheres, but gas planets cannot have civilizations. Of the solid worlds, only Earth and Mercury have magnetospheres, and Mercury is too weak to stop the solar wind because of its closeness to the sun. Another protective shield that keeps the Earth safe from the sun is its atmosphere. The atmosphere is about 300 miles thick, with most of it concentrated within just 10 miles of the Earth's surface. The atmosphere protects life on Earth from both the sun's ultraviolet, UV, radiation, and X-rays. The gas, ozone, which is 3 oxygen atoms bound into a large gas molecule in the upper atmosphere, blocks most of the sun's UV radiation from reaching the ground. The planet Mars, whose atmosphere is 1,000 times thinner than the Earth's, has no ozone, and the sun's ultraviolet emissions have totally irradiated its surface. A planet must be able to stop the UV radiation from its star, so the specific composition of the atmosphere is critical for any planet to have an intelligent civilization. We've got it. but it is a rare and precarious mix. The planet must have some part of its surface solid to walk and work on. The planet must have a crust. It's pure science fiction to consider underwater civilizations or floating civilizations in the atmospheres of other planets. A planet's crust must have tectonic plates that move. This movement of tectonic plates creates the subduction of the crust. Subduction is when one tectonic plate slides under or over another, bringing the fresh matter to the surface. This renewal of the chemical properties of the planet prevents chemical equilibrium, where nothing is reactive. Earthquakes and volcanoes also contribute to the process of geochemical renewal. That's right, earthquakes and volcanoes are good. Subduction of tectonic plates, then, is another planetary essential for life. Mars doesn't have tectonic plate activity. Neither does Venus nor Mercury. Mercury is one big tectonic plate, but there's no ongoing plate activity other than slight shrinkage. One big reason these planets have no life is that there's no geochemical reactivity because there's no tectonic subduction. And that brings us to the Moon. Yes, the Moon. To say that the Moon keeps us alive may seem like a stretch, but the contribution of the Moon to life on Earth is essential. First, the gravity of the Moon as it moves through space with the Earth not only makes the ocean tides ebb and flow, it also helps the rotation of the Earth to churn or stir the magma inside the Earth. The motion of the magma inside the Earth, with its high metallic content, contributes to the creation of the Earth's magnetosphere. So, the Moon keeps us safe in space by helping Earth become a geodynamo and creating our magnetism. The Moon is the largest moon in the solar system compared to the size of the planet it orbits. Essentially, it's primary. Many people consider the Earth-Moon system to be a double planet, but that's another issue. Another thing the Moon does that keeps life safe on Earth is to hold the Earth steady. Because the Moon is gravitationally locked to the Earth, the Moon acts much like a balance pole does for a tightrope walker. Therefore, the Earth doesn't wobble very much compared to other planets. This wobble is called libration. If the Earth wobbled as much as Mars or Saturn, not only would our weather become chaotic, but farming might have been impossible. These rare or unique astronomical circumstances work together to make Earth habitable for humanity. Many other factors are not astronomical, such as evolutionary, biological, and chemical factors required for life to exist on Earth. The probabilities, or improbabilities, are multiplying. Taken all together, we are very, very lucky to be here. In fact, we're so lucky that we may have hit the jackpot. Considering all the possibilities, it's doubtful that anywhere else in the universe is as fortunate as Earth.
Bang. That's how it all started, around 13.8 billion years ago, and was figured out over the past 100 years. Everything we see in space today – planets, asteroids, comets, stars – it wasn't there at the beginning. In the 1920s, astronomers came up with the idea of how a long, long time ago, the universe was just a single point, an extremely hot, like trillions of degrees hot, compact, dense point that stretched and expanded unimaginably fast. Matter that started flying in all directions at the speed of light at one particular moment. The Big Bang was complete chaos, with teeny-tiny particles that were mixed with energy and light. Yes, a total mess, but still, in the first minute after the Big Bang, the base for everything that would later appear was almost finished. It was hot only during this huge blast. As soon as the expansion started, the universe began to cool down, similar to when gas cools when you spray it from an aerosol can. During that process, part of the energy kind of froze out, just like the water freezes into ice. Here, pure energy got frozen and solidified into matter. 1 minute after the bang, the cooling thing was still going on, extremely fast and literally everywhere at once, since the universe really doesn't have edges. It wasn't just a compact dot anymore. The base for further expansion and all that's coming was being formed. Remember those tiny particles from that first boom stage of the universe? They started grouping together, which formed atoms of helium and hydrogen. It took about 3 minutes for most of the helium and all of the hydrogen in space to be made. These two are the most common elements and the basic materials that later formed the first galaxies and stars. Just because the base wasn't finished doesn't mean the creation of the universe stopped after those first couple of minutes. True, after that, no new elements were created for millions of years, which is why the initial version of the universe was entirely helium, hydrogen, and energy. But eventually, atoms began to slowly group together, which, after lots and lots of time, caused the creation of galaxies and stars. Clouds of helium and hydrogen grouped and turned into stars that had gravitational forces. Our Sun is also made of 3/4 hydrogen, while the rest is helium. 1/4? Yeah. At later stages, some other, heavier elements started to show up too, such as carbon, iron, oxygen, and so on. It wasn't all about chemical processes where new elements, stars, or planets kept coming. The whole universe has been expanding ever since the Big Bang. Researchers realized other galaxies are kind of moving away from ours. Guys, you need to stop doing that. How will we discover alien life out there if you keep running away all the time? And not just that. The farthest galaxies are actually moving quicker than the ones closer to our galaxy, the Milky Way. The universe is fabulous, unknown, mysterious, scary, and completely silent. Imagine yourself floating in your spacesuit somewhere above Earth. All you could actually hear is the sound of your own breathing, nothing from out there. Since there's no atmosphere, sound doesn't have a way to travel or be heard. Speaking of spacesuit, that thing costs around $12 million. I guess that means we'll have to wait up a little bit more to try that whole chilling in space thing. Mercury is the closest planet to the Sun, so you might think it's the hottest one too. And yet, Venus actually takes the title of the hottest planet in our solar system, with the surface baked by a temperature of 840 degrees Fahrenheit. Fair enough. Mercury doesn't have an atmosphere, which is in charge of regulating temperature, so it loses the race for the title of the hottie of the solar system. Venus also has pretty long days. Just one takes around 243 Earth days. Now that comes in handy for those people with pretty long to-do lists, who like to take it easy and slow. However, Venus orbits the Sun in 225 Earth days, which means 1 year there lasts 18 days less than a Venus day. You can have 2 birthdays in one day then? Well, 2 birthdays in a day could be one of the good sides, but the downside is that on Venus, it rains sulfuric acid and snows metal. Not so fun anymore, huh? The Earth is cool itself. Being 4.5 billion years old and the only known planet that supports life, it also has more trees than there are stars in the Milky Way. 3 trillion, while there are only 100 to 400 billion stars. We may have counted trees, but still, so little do we know about our ocean. Only 5% of it is explored, so we know less about it than about Mars or the Moon, whose surfaces have been fully mapped. It's funny how outer space is just 62 miles away from us, counting from above sea level on our planet. Seems so close, I sometimes go that distance just to have my breakfast. And yet, only 5% of the universe is visible from Earth. 68% of it is dark energy, while 27% is dark matter, which we can't see with a telescope. So close, yet so far. We will always see the same side of the Moon no matter where we are on Earth. The Moon rotates on its axis at the same speed it orbits the Earth. This is called synchronous rotation. Sunsets on Mars are blue. That happens because the fine dust on the red planet has the size perfect for blue light to efficiently penetrate the atmosphere of Mars. So the blue light scatters, after which it stays closer to the direction the Sun goes, unlike the light of other colors. The universe is full of wonders, and one of them is a planet made of diamonds. Yay! It's twice bigger than the Earth, and scientists believe it's mostly covered in diamond and graphite. Now to get there, you might probably need that $12 million spacesuit, together with a really expensive ship. But if, and that's the key word here, you manage to go there and back, you may even easily pay it off. Scientists also have some predictions as to the end of everything. Oh boy, ready for this? At its early stages, the whole universe was dense and compact, so it was really thick. But after around 400,000 years, it kept expanding, which made it more transparent. All of this encouraged releasing light we know today as the cosmic microwave background, or CMB. It's like if you turn your TV on an empty channel and switch off the cable, you'll see the static black and white dots moving on your screen. There's something like the CMB, and also an afterglow of all that energy that was released during the Big Bang. CMB is still here. Astronomers can see it through the microwave telescope. Expanding never actually stopped. The universe is still spreading every second at an unbelievable speed, causing all the objects in space to move away from each other all the time. How repelling! We know it because the Sun from other galaxies appears redder than it's supposed to be. This is called redshift, and it happens when the source of light moves further from the one who's observing it. Then there's gravity. It attracts all objects in the universe to each other, which is the reason why planets keep orbiting the Sun, or why our solar system orbits the center of the Milky Way. It's why we stay on the ground, while in space we'd float since there's no gravity up there. Having all this in mind, scientists got the idea that one day the universe will simply take the opposite direction and start shrinking back, which will be known as the Big Crunch. Whether this really happens depends on the type of our universe. If it's open, it'll keep expanding and nothing will ever stop it. But over time, as it's stretching, the density will become so low, galaxies won't be able to form new stars, and the existing ones will fade away. When space loses all the light and heat, life won't be possible. The universe will just remain as a cold beyond, which will keep spreading thinly into endless darkness. And then, Big Crunch or not, bang! It all disappears. Hey, good thing we have billions of years ahead of us, huh? Well, maybe you. I won't be around then. I'm going to retire.
Boom! It was an epic space explosion that made scientists' hair stand on end when they discovered it in February 2020. Its size and power are enormous, even by cosmic standards. We set our destination to a group of galaxies in the Giraffe constellation. If our rockets could fly at the speed of light, as fast as it takes the light from the bulb in your lamp to reach your eye when you switch it on, zoom, instant, it'd take 2.6 billion years to get where this explosion occurred in space. 2.6 billion years. A lot's happened in that time here on Earth. That long ago, dinosaurs weren't even around yet. Primordial life was just leaving the ocean and heading on land. Well, we're traveling faster than the speed of light, and we reach our destination, ground zero, for a boom so big it'd be like 600 million suns exploding simultaneously. And our sun is massive to begin with. It could fit 1 million Earths inside. In fact, 99.8% of the stuff that makes up our entire solar system is the sun alone. The remaining 0.2% is all the planets, moons, asteroids, and other random cosmic bodies floating around our star. And here's the real kicker. This burst lasted 100 million years. That's from today's digital world with smartphones and self-driving cars, all the way back to dinosaur times. So what set off this space boom of epic proportions? A black hole. What else? This monster swallowed so much substance that it choked and shot out a bunch of plasma beams. They cut through space and formed a cosmic wasteland all around the site. It was thought to be the biggest explosion in the universe. But sooner or later, every record gets broken. We head to another galaxy cluster. This one, dubbed Ophiuchus. An explosion thundered in it 5 times more powerful than the one in the Giraffe. It was so big, you could easily line 15 Milky Ways across its blast area. Mind you, our galaxy is over 100,000 light-years across and home to 200 billion stars. Yeah, whoa is right. It was the largest space blast since the Big Bang that started it all 13.8 billion years ago. So what was the source of this blast? To answer that, we'll need a simple analogy. Just like on Earth, space sort of has its own megacities. These New Yorks and Tokyos of the cosmos are massive. And that word doesn't even do it justice, but I tried. They're officially called superclusters of galaxies. At the center of the most mega huge ones, you'll find a supermassive black hole. Now, scientists still don't know much about them, but the theory goes that they're essentially a whole bunch of stuff, or matter, that gets squeezed into a teeny tiny point that can't even be measured because it's infinitely small. Yeah, complicated stuff. Think of it this way. It'd be like taking the entire Earth and shrinking it down to the size of a grain of rice. That grain of rice would still weigh the same as the planet. All that stuff would just be really squished together. So more matter equals more gravity, meaning a black hole's pull is unescapably strong. Not even light can get past it, hence the whole black part of its name. Funny thing is, we can't even see them with our eyes. Black holes don't glow or reflect light. They just swallow it up like spaghetti. Ugh, makes me hungry just thinking about it. But back to epic space things that go boom. A supermassive black hole exploded in this Ophiuchus supercluster of galaxies. This monster stopped pulling in everything around it like black holes usually do. Quite the opposite. It started spewing stuff out. A colossal stream of plasma ripped through space almost at the speed of light and broke through a bubble 1.5 million light years across. Every thousandth of a second, it was like 20 billion megatons of TNT went off, and it continued doing that for 240 million years. But now, I draw your attention to the heavyweight of the Milky Way. It's the toughest guy in the galaxy, a supermassive black hole called Sagittarius A star. The mass of this beast is 4 million times that of the Sun. And you'll like this, it's only 25,000 light years from our home planet. In space terms, this thing is pretty much like our neighbor 2 houses down the street. Wait, don't worry, no need to pack up and move. Our neighbor has given up his old business of shooting hot jets into space. But in 2019, he did make astronomers' hearts skip a beat. Near this Sagittarius A star, they noticed a flash that was 75 times higher than normal. Their theories: 1. The hole swallowed up part of a star that found itself wandering way too close for comfort. Or 2. A gas cloud crashed into it. After a 14-hour spike in activity, Sagittarius A star finally calmed down. Phew! But in the past, this giant was quick-tempered and knew how to light space up. 3.5 million years ago, our very ancient ancestors, as in they weren't technically human yet, were already walking across Africa, innocently unaware of a cataclysm happening far off in the sky above them. It looked like a beacon that suddenly turned on and shot out 2 cone-shaped beams. The whole thing was triggered by a hydrogen cloud 100,000 times more massive than the Sun. It came too close, and Sagittarius A star reacted. Those jets of plasma cut through space for 200,000 light years. They didn't stop for another 300,000 years. That's the snap of a finger on the cosmic scale, but astronomers still find traces of that boom even today. Neutron stars also know how to set off some fierce fireworks. They appear after giant stars run out of fuel and collapse in on themselves. Imagine the entire sun getting squished down into the size of a small city. Yep, that makes neutron stars incredibly dense and heavy. 1 teaspoon of their matter weighs around 10 million tons. They spin extremely fast, hundreds of full rotations a second. And for some of them, they shoot out energy beams from the poles, making it look like a cosmic lighthouse. One of the most interesting neutron stars is in the constellation Sagittarius. Like black holes, it has powerful gravity and pulls in tons of matter. This all collects in a massive rotating disk. This particular one was powered by hydrogen from a nearby star. It gulped up its neighbor, taking in so much matter that it started heating up. The result? A gigantic fireball launched from its surface. Astronomers witnessed this on August 20th, 2019. They saw a 20-second flash that lit up space. It was the brightest burst NASA has ever seen. The star spent more energy on it than the sun produces in over a week. But of course, nothing beats the biggest boom of them all, the one that brought life to our entire universe, according to the most popular theory. But first, a little backstory. Scientists say only 5% of the universe is stars, planets, asteroids, comets, dust clouds, you, me, your chinchilla, all life, basically all the stuff you can see with your own eyes. So what can the remaining 95% be? The mysterious and dubious sounding dark energy and dark matter. In simple terms, they're like the yin and yang of space. Dark matter makes things attract to each other with gravity. It's the glue of our universe, keeping everything together. Dark energy does the opposite. It makes things repel and grow further apart. So the theory goes. And weirdly enough, dark energy makes things grow further apart the farther they are from each other. Scientists can even see this for themselves. The more distant a galaxy is, the more quickly it's moving away from Earth. But those two forces weren't always around. In fact, about 13.8 billion years ago, there wasn't anything around. Everything was condensed into a teeny tiny dot that's infinitely small. Sound familiar? Yep, this mysterious, forever shrinking point is also in the center of black holes, and it's called a singularity. It's where all our fancy science and math breaks down. It's the most puzzling thing out there. But one day, that incredibly dense and hot point started to expand in all directions, and it grew faster than the speed of light, doubling its size 100 times within a fraction of a second. If you want the specifics, it was 100th of a billionth of a trillionth of a second. Yeah. The more time passed, the faster and bigger it grew, and it's been expanding since, like blowing up a balloon that never pops. Scientists called this expansion the Big Bang.
Now, it's been a long time since there was a supernova in the Milky Way. Over 400 years to be precise. So hey, we're long overdue. So here are the most likely stars to go boom, if they haven't already. At the top of the list must be the Southern Hemisphere star Eta Carinae. Greek letters before the name of the constellation indicate the rank of the star's brightness in that constellation. Sir Edmund Halley, in 1677, recorded Eta Carinae as the seventh brightest star in the constellation Carina, Eta being the seventh letter in the Greek alphabet. It might not have looked very bright to Sir Edmund and his contemporaries in the 17th century, but modern studies of Eta Carinae estimate it's 5 million times more luminous than our Sun. Luminous is a technical word astronomers use. It doesn't just mean brightness. Luminosity refers to the total energy released at all frequencies. Eta Carinae releases 5 million times more energy than the Sun. Truly one of the whoppers of the Milky Way, Eta Carinae is 100 times more massive and 240 times larger than our yellow-white dwarf sun, Sol. Obviously, since it appears dim, Eta Carinae is pretty far away, about 7,500 light-years away. Yet even at this distance, if this star goes hypernova, it can still impact Earth's ozone layer, disrupt satellite communications, and harm astronauts. 159 years after Halley's observation, Eta Carinae experienced a nova-like explosion. It increased from a relatively dim star to become the second brightest star visible from Earth, but only for a period of 27 years. From 1836 until 1863, Eta Carinae was the second brightest visible star after Sirius, the dog star, and Sirius is only about 8 light-years away. Since 1863, aside from a couple of flare-ups, Eta Carinae has dimmed back down to its original brightness at magnitude 4.5. Now, astronomers owe us a small apology, which we don't expect to get anytime soon, for star magnitude nomenclature. The brighter a star is, or planet, or moon, the lower its magnitude. Thus, stars brighter than first magnitude are either 0 magnitude or negative magnitude. The full moon, for example, is magnitude negative 13. A magnitude positive 4.5 star, like Eta Carinae, is quite dim as seen from Earth. but it's clearly visible in a night sky without light pollution or clouds if you live anywhere south of the latitude of Cairo, Egypt. 30 degrees north latitude is the farthest north you can see this star. Now, listen up. Eta Carinae is currently up to something. It's been brightening again and is now brighter than at any time since 1864. It's a complex situation. Eta Carinae is really two stars, Eta Carinae A and Eta Carinae, what's your guess? Oh, B. There's a third star nearby that's also interacting with the double star's dynamics. Now, without looking, I'm guessing it's named Eta Carinae C. Good guess. Blown out into two incredibly massive globes of gas that are expanding at 20 million miles per hour, Eta Carinae is, without a doubt, one of the strangest looking stars you'll ever see. Remember, it's located at a great distance of 7,500 light-years away from us. And if anything had happened to Eta Carinae in the last 7,500 years, like going hypernova, we wouldn't be able to see it, because none of Eta Carinae's electromagnetic radiation would have gotten here yet. Astronomers are keeping a close watch on Eta Carinae because it can go hypernova at any time. Or maybe it already did 5,000 years ago, in which case we'd only have to wait another 2,500 years to see it. Yeah, like I'll put it in my planner. Now, from a list of over 30 likely candidate stars that might go supernova, Rho Cassiopeiae is many astronomers' choice. Another Greek letter, Rho, is the 17th letter in the Greek alphabet. It means that Rho Cassiopeiae is the star with the 17th brightest apparent magnitude in the constellation Cassiopeia. Yet Rho Cass, a nickname, is only one of 7 known yellow hypergiant stars in the Milky Way. It's another whopper. To be seen at magnitude 4.5 from a distance of about 10,000 light-years away, Rho Cass must be a very large star, a hypergiant. Placed where the Sun is, Rho Cass would encompass the orbit of Mars. But it's still yellow. It's not a red giant star. Red indicates a cooler surface temperature. Rho Cass, as huge as it is still as hot on its surface as our Sun, or even a little hotter. That can only mean two things. Deep inside its core, Rho Cass is fusing atoms much heavier than hydrogen or helium. Plus, Rho Cass is producing much more energy than a red giant star. In the year 2000, Rho Cass erupted massively. It brightened by 2 orders of magnitude as it ejected 10,000 times the mass of Earth into space at 4 times the speed of sound. Astronomers detected the signature of titanium oxide in this eruption. This means that Rho Cass is much closer to going supernova, or in this particular case, hypernova, than astronomers used to assume. Iron is just a few steps above titanium in the periodic table, and when iron forms, fusion stops and a star collapses. Rho Cass is really close, or more correctly, was really close. Because the eruption we saw in the year 2000 really happened 10,000 years before, many astronomers think Rho Cass has already gone hypernova, formed a black hole, and doesn't even exist anymore. Meanwhile, Betelgeuse caught everyone's attention not so long ago. The star, not the movie. It dimmed dramatically, appearing only 37% as bright as it usually is. Is it getting ready to go supernova? Betelgeuse is by far the brightest star in the whole sky, in infrared light. This is an important fact because it relates to Betelgeuse's status as a supernova candidate, as we shall soon see. Betelgeuse is also named Alpha Orionis, another Greek letter designation. So we should conclude that Betelgeuse is the brightest star in Orion, right? Wrong. It's the second brightest star in its constellation. Rigel, or Beta Orionis, is the brightest one in that region. Yeah, figure that one out. It may be because Betelgeuse is classified as a semi-regular variable star, which sounds kind of redundant to me. Its approximately 400-day cycle of pulsation changes its brightness by about 1 full magnitude, going from much brighter than a first magnitude star to closer to a second magnitude star. But never was Betelgeuse observed to dim so rapidly or so drastically as it did recently. So what's going on with it? Well, from late 2019 to mid-2020, Betelgeuse went through a period of substantial dimming during a mass ejection event. The world astronomy community jumped on the situation, and in the course of their investigations, they came up with some surprising new factual data on Betelgeuse. First, Betelgeuse is not as far away as we once thought. The new, more accurate distance for Betelgeuse is 548 light-years. That's 25% closer than previously measured. The second new fact, Betelgeuse's diameter has been reduced by the same percentage. The star is now known to be 25% smaller than previously believed. The cause of Betelgeuse's dramatic dimming was also determined. The giant star ejected a cloud of gas that contained magnesium. The cloud blocked a large portion of the light coming from Betelgeuse and made it appear visually much dimmer than it really was. Magnesium is not halfway to iron on the periodic table, which means Betelgeuse is not as far along on the path to a supernova as was suspected previously. When iron starts forming in a star, it means that this star is close to shutting down its fusion reactions. The next step is implosion. We aren't quite there yet with Betelgeuse. This star emits most of its energy as infrared light, and it also indicates that its core is most probably still burning helium, and not something that would greatly increase the amount of heat, like carbon for instance. Betelgeuse will still go supernova, but not for another 100,000 years. So you can cross it off your supernova list for the time being. And as for how to correctly pronounce Betelgeuse, you can say it any way you like. There are as many different pronunciations out there as there are people who think they know how to pronounce it correctly. Now, supernova 1987A caught astronomers off guard when it lit up the large Magellanic Cloud 100,000-plus light-years away from the Milky Way. That's when attention was turned to a similar star much closer to Earth, Rigel, in the constellation of Orion. Could Rigel surprise us and suddenly go supernova? There's something called the supernova problem that you should, probably know about because it may relate to Rigel going supernova or not. It seems that stars over 17 solar masses don't always go supernova. Recently, a red giant star simply vanished. Once again, it didn't go supernova, it disappeared. This had often been happening in computer simulations of supernovae, and now it finally occurred in real life. Rigel's mass is 21 solar masses. In other words, it's 21 times more massive than our Sun. So, will Rigel go supernova or simply vanish into a black hole that it'll create in its core? Astronomers and physicists continue their work of learning more about the dynamics of massive stars, scouring the sky for the next supernova in the Milky Way. Meanwhile, we can rest confident that we on Earth are in no danger from the harmful effects of nearby supernova explosions. We live in a nice, quiet, peaceful, stellar neighborhood, except for those Martians next door.
You're traveling through deep space, circling stars and entire galaxies. Whoa, looks like this multicolored nebula will soon collapse under its own weight and explode like a supernova. Now let's carefully circle this black hole. Try not to get caught in its gravitational field, or it'll swallow you like a space monster. Wait, what's that strange structure right there? It's a glowing wall. And if you look closely, each glowing dot is an entire galaxy. That wall has about 100,000 of these galaxies. The Milky Way has 100 billion stars. So this wall holds a quadrillion, that's 10 followed by 15 zeros, of stars like our Sun. This giant structure is called the South Pole Wall. It's located about 500 million light-years from Earth. By comparison, the closest star to our home is Proxima Centauri, and it's about 4.2 light-years away. Rockets can cover that distance in about 73,000 years, so the journey to the South Pole Wall may take longer than our solar system exists. And this wall is simply gigantic, even on a cosmic scale. It's about 1.37 billion light-years long. To give you an idea of how large that is, the Milky Way is only 100,000 light-years wide. But you can't see this wall even with the most powerful telescope. The problem is that the Milky Way itself obstructs your view. It's so bright that it's hiding this wall. It's like trying to look at the starry sky in a metropolis. The light pollution won't let you do that. Scientists have been able to detect this galactic wall by measuring redshift. We know that all objects in the universe are moving. They spread out from each other as a result of the Big Bang, which happened billions of years ago. And when galaxies move, their light waves change slightly. By measuring this change, we can understand what the object is and how it moves. And this wall isn't even the largest in our universe. This is the Hercules Corona Borealis Great Wall. It's a giant flat superstructure about 10 billion light-years wide. That's around 10% of the entire observable universe. And it's also a wall. That is, a cluster of galaxies. We were able to detect this giant structure by gamma-ray bursts. It's the brightest electromagnetic event in the universe. You could even see it in the far reaches of our universe. Such bursts are a very rare event. In the Milky Way, for example, it happens once every few million years. If we notice many such bursts in a short time from the same place, it means that there are many objects like the Milky Way in that place. So, there are a lot of galaxies out there. Another unusual giant structure in the universe is the huge, large quasar group. It's about 4 billion light-years across. So it takes a photon of light almost as long as our planet has existed just to get from one side of the structure to the other. And if you put the huge, large quasar group on the scale, it would be 6.1 billion times heavier than our Sun. Scientists have found that there are at least 73 quasars in that structure. These are some of the most unusual objects in the universe. They are the active cores of galaxies. At the center of a quasar is a supermassive black hole. This giant eats up the matter around it. A wild force of gravity twists the matter around the black hole, forming a disk. And this disk is the source of the strongest radiation out there. By comparison, the radiation from a single quasar is tens or hundreds of times stronger than that of all the stars in our galaxy put together. Because of such strong radiation, we can detect quasars, even at very long distances. That's why they're also called beacons of the universe. Scientists use quasars to study the universe and the movement within it. One of the most distant quasars from us is about 13.1 billion light-years away. This makes it one of the oldest objects in the universe. It appeared about 690 million years after the Big Bang, and it's almost 3 times older than our solar system. It's still glowing with extreme brightness, about 4 and 14 zeros times brighter than the Sun. Scientists explain that at the center of the giant is a supermassive black hole, 800 million times heavier than the Sun. All these giant structures are just building blocks of our universe. Look, this is our solar system. Now, zoom out a little, and this is where our home star is in the Milky Way galaxy. Zoom out again. Here's a local group of galaxies. All the bright spots here are galaxies. Here's Andromeda, and here's the Triangulum galaxy, plus a few dozen other slightly smaller galaxies. They're all gravitationally connected. The size of this structure is about 10 million light-years. That's 100 times the width of our galaxy. Zoom out, please. This one is the Virgo supercluster. It's 20 times larger than the local group. There are about 30,000 different galaxies, and the mass of the whole thing is about 1 in 15 zeros solar masses. Zoom out again. Laniakea. This structure is almost 3 times larger. It includes the Virgo supercluster and other smaller clusters. And there are about 100,000 galaxies here. It's not over yet. Zoom out one more time. Here's the Pisces-Cetus supercluster complex. This giant galactic structure contains about 60 clusters of galaxies. So there are more galaxies in it than grains of sand in the desert. You know what to do. Zoom out! Phew. This is the observable universe. There are over 500 billion galaxies. And the stars? Well, there are about 1 billion trillion stars. The observable universe has its own structure. Clusters of galaxies form chains and walls, as you've seen before. But these strands are separated by huge regions of absolute emptiness. These areas are called voids. In these places, there is no matter at all. There are fewer molecules in the voids than in an empty room. One of these voids has a very mystical reputation. It's the Eridanus supervoid, or the cold spot. It appeared here only 380,000 years after the Big Bang. It's almost 1 billion light-years wide and could hold hundreds or thousands of galaxies with trillions of stars. Some scientists believe that this cold spot may have been the result of the largest collision ever, a collision of universes. There's a theory that our universe is some kind of bubble, a huge sphere that contains all these walls and chains of galaxies. Now imagine that there's an infinite number of these bubbles. They could be parallel worlds or different universes. Many years ago, one bubble came close to the bubble of our universe. Their walls touched, and the two universes connected for a while. It's like two drops of water coming together. But that universe kept moving. The area where the bubbles joined became thinner and thinner until that connection broke, and the two bubbles detached from each other. At this point, the second universe ripped some of the material out of our bubble. All those galaxies that used to fill the Eridanus supervoid ended up in a parallel universe. Scientists supposed we might travel through other bubbles. Flying to the supposed wall of our universe would take forever, and then it would take even longer to fly through interuniversal space. So we have to use portals, or wormholes. Here's how it works. Imagine a piece of paper with point A on one side and point B on the other. Instead of moving all the way across the sheet of paper, we just fold the sheet so that point A is right above point B. All that's left to do is make a small hole, and the journey takes only moments. Some scientists believe that such shortcuts through universes lie inside black holes. But how do you survive falling into a black hole? You just have to pick one that's big enough. It's all about gravity. Imagine you're falling into a black hole right now. The closer you get to it, the stronger effect it has on you. It intensifies with every inch. At one point, the gravitational force that affects your head is much stronger than the one that affects your feet. Then you turn into spaghetti. Yum. But if you choose a supermassive black hole, like the ones at the centers of galaxies, the gravitational force in them increases gradually. They can be millions of times heavier than the sun and much bigger, but the gravitational force on your head and your feet will be almost equal, and you will still feel comfortable. Who knows? Maybe if you manage to survive a fall into such a massive black hole, you'd find yourself in a completely different universe where different laws of physics apply. But so far, this is just a theory.
This is our home planet Earth and its satellite, the Moon. Zooming out, and here's our solar system. A bit more, the Milky Way galaxy. And we're a small dot among an infinite number of stars. Now, even farther out, a cluster of galaxies. Dots and swirls in the endless space. Further, there's Laniakea supercluster. That little dot here is our galaxy. Moving on, Hydra Centaurus supercluster. Huge clusters comprising thousands of galaxies are no more than a speck from here. Next, Pavo Indus supercluster. This is an area 200 million light-years wide. We can zoom out until we see the entire observable universe. Each little dot in here actually contains thousands of galaxies and quadrillion stars. Scientists speculate that our universe may look like a bubble, and that bubble might collide with another universe. Yes, other universes could exist. Actually, even a whole infinite number of those. All of them could have appeared after the Big Bang. The collision between them isn't impossible either. At least, it might have happened before. And the proof is here, in the direction of the constellation Eridanus. This place is called Eridanus supervoid. It's about 1 billion light-years wide. By comparison, the width of our entire galaxy is only about 100,000 light-years. There's absolutely nothing in this place, and it may be a trace from an old collision between our universe and another. Scientists think they were passing by each other. When the distance between them was minimal, the gravitational forces of the bubbles began to pull toward each other, just like two drops of water trying to connect when they're close. But the speed of the universes was too high for them to continue interacting, so the other universe just tore out a piece of our bubble. There might have been about 10,000 galaxies in that void, and all of them were either destroyed or taken over by the other universe. Let's travel to the edge of our universe to see how this collision might have taken place. We're 10 billion light-years away from our home. Here, in another galaxy, we see amazing nebulae of different colors and shapes. And if you look in the other direction, there's a huge wall moving at us. All these bright sparks on it are enormous galaxies about to collide with us. But in fact, it's a humongous mirror that only reflects our universe. Here, space-time is distorted and begins to be pulled into another universe at a tremendous speed. The usual law of physics may simply stop working at this point. Gravity may disappear, and with it, all the stars would explode and people on the surface of planets would hang in weightlessness. But if the universes didn't go at a tangent but crashed directly into each other, things would be much scarier. The enormous amount of collision energy would probably cause an incredible explosion. Its force would simply destroy everything in our bubbles. Still, the two bubbles might begin to merge too. At first, all galaxies at the edge of the universes would be torn apart. But then, the merger would begin. The galaxies would start moving chaotically. They would fly past each other, break apart, collide, and explode. The collision of two galaxies is an accident of enormous proportions, and it might happen to our home quite soon, in space terms. The Andromeda Galaxy is heading our way. It's a spiral galaxy about twice the size of ours, and there are about 1 trillion stars there, which is twice more than in our Milky Way. At the very center of this bright galaxy lurks a dark beast, a black hole. Its weight is 2 8/8 of the Sun's mass. Red giants hundreds of times larger than our Sun. Pulsars emitting enormous amount of energy like spotlights. Rogue stars, and many large and small black holes. This soup of dangerous objects is moving toward us at 68 miles per second. A trip to New York to Los Angeles at that speed would only take half a minute. The disk of Andromeda can already be seen with the unaided eye on moonless nights. As time goes on, it'll get even bigger. As Andromeda gets closer to us, its gravitational force will begin to stretch the arms of our spiral galaxy. It'll begin to unwind. The stars and planets will lose their orbits. One possible scenario is that an unknown asteroid, or even a dwarf planet from the Andromeda Galaxy, will crash into the Earth at an incredible speed. Our planet will explode just like a balloon from this impact. Oh, goody. Another option involves stellar collisions. Our Sun would face another star. The bigger star will slowly begin to consume the smaller one. First, it will steal the light upper layers from it, and then it will eat it just like spaghetti. Or even like rigatoni. When a large star reaches its critical weight, it will burst. This explosion will destroy everything around it, including our solar system. Perhaps the shockwave will even reach other neighboring stars. Yet another scenario is that our solar system will be thrown into dark space. Imagine a tennis ball tied to a rope. You take the rope and spin the ball over your head like a sling. Then you let go of the rope and send the ball flying. This is what will happen to the Sun and all the planets around it. We'll find ourselves in dark and cold space. But life on Earth will not be affected. We'll still have our bright star to keep us warm. The only disadvantage is that all the stars in our night sky will disappear. And the most likely possibility is that the merger of two giant galaxies will have no effect on us at all. The thing is, the distance between stars and planets in space is enormous, so they can all just mix together and form one giant cloud. It would be like shoveling fine sand through a big sieve. The objects won't interact with each other. But the most interesting thing will happen to the black holes in the centers of our galaxies. Right now, there's a dense cluster of stardust and stars around them. As Andromeda and the Milky Way come closer together, they will begin to dance with each other. Gee, will it be the twist or the foxtrot? And when the black holes get close together, they'll begin to swallow all matter around one another. Billions of tons of colored stardust, asteroids, and star particles will fly toward the very center of either black hole. It might seem like this process happens very slowly, but it's an illusion. Super heavy objects like black holes warp the space-time grid, so time is much slower near black holes. And all objects that seemingly stay on the event horizon for weeks or even months are actually long gone. When the black holes finally come together, they merge into one supergiant black hole, but its mass is slightly less than the combined mass of the two dark monsters. Some of their weight is transformed into collision energy. This energy is released so strongly that its waves can be felt in other galaxies. Now, a huge black hole gathers all this dense and hot core of the two galaxies around itself. At some point, the black hole feels full and throws out powerful jets of energy into space. This is called an active galactic nucleus. It's one of the brightest phenomena in the universe and the most powerful source of electromagnetic radiation ever known. These jets may be more than 5,000 light-years long. By comparison, the distance from Earth to the nearest star, Proxima Centauri, is only 4.2 light-years. And the explosion that accompanies the jets has the power of 100 supernova explosions. Wow, blows my mind. The blast wave from this event could even reach the edges of a new galaxy, and this outburst would be visible from millions of light years away. Now, there are dense clouds of multicolored dust at the center of merged galaxies. The weight of these clouds is so great that they begin to shrink and take on a round shape. Gradually, they become so heavy that they compress the core and nuclear reactions start inside them. The temperature begins to rise, and soon, boom, there's a supernova. It's a veritable fireworks show at the center of the galaxies. Stars erupt from the fog and form new hot worlds. At this point, the arms of the two galaxies that were previously pulled out slowly return to their former shape. The super-heavy center of our galaxy has such a gravitational force that it affects stars and nebula hundreds of thousands of light years away. The galaxy's arms twist again, and we see the new and finished galaxy, the Milkomeda, or Milkdromeda. Hey, how about the Milky Meter way? Blah blah blah. Well, that's hard to say.
The morning is cloudy, but it isn't raining. So you grab your bag and head off to work. You're halfway there when it starts drizzling. Then raining. Then pouring. There's only one thought in your head as you're dashing through wet streets towards your office building. If only I could hop in a time machine and go back in time. I'd have put that umbrella in my bag. Unfortunately, going back in time is not possible. But guess what? We still managed to travel in time. But let's start from the very beginning. More than 100 years ago, a famous scientist called Albert Einstein, I bet you've seen his most popular photo, came up with a theory about how time works. He gave it a nice little scientific name, the theory of relativity. According to it, space and time are linked together. Another point is that our universe has a set speed limit. Nothing can move faster than the speed of light, which is 186,000 miles per second. Okay, you may say, but what does it have to do with time travel? Well, the theory of relativity also claims that the faster you move, the slower you experience time. And several experiments prove this to be true. For example, let's say you have two clocks set to the exact same time. You leave one clock at home and take another one with you while traveling by plane. What's important here is the fact that the plane is going in the same direction as Earth. After your plane finishes its flight around the world, you can compare the time on the two clocks. You find out that the clock that traveled with you is a bit behind the clock that remained on the ground. Because of this, GPS clocks are corrected. GPS satellites travel around our planet at tremendous speeds, around 8,700 miles per hour, and more than 12,000 miles above the surface of Earth. This speed slows GPS satellite clocks down, but the altitude speeds them up. As a result, the clocks on GPS satellites experience time at a rate that is slightly faster than 1 second per second. And if this difference in time wasn't corrected, you wouldn't be able to use GPS to figure out your exact location. In any case, this is probably the closest thing we have to time travel. You see, our planet is constantly moving around the sun at an average speed of 67,000 miles per hour. The sun, along with the entire solar system, is, in turn, circling the center of our home Milky Way galaxy at a staggering 140 miles per second. And the Milky Way itself is also moving. It's spinning at a speed of 130 miles per second. Those are some really dizzying numbers. And now imagine that in order to get to the past, all this space matter must also turn back and return to its original position. Just admit it, it's absolutely impossible. By the way, even though we can't exactly travel back in time, we can look at the past, thanks to NASA's space telescopes. They help us see stars and galaxies that are insanely far away. It takes the light coming from them ages to reach Earth. That's why when you observe those distant worlds, you see what they looked like a long time ago. Now, what if time travel was somehow possible? Wouldn't all the fun be spoiled by the time travel paradox? You know, like finding yourself in the past and accidentally preventing your parents from meeting each other? The problem is that Einstein's theory of general relativity theoretically allows a person to travel back in time and come in contact with their past self, which can potentially endanger their existence. But you can breathe out. Some scientists at the University of Queensland have recently claimed that this paradox might not actually exist. They say that even if you made some changes in the past, the timeline would self-correct anyway. In other words, it would still ensure that whatever event sent you back in time would still happen. One more study claims that even if some changes happened in the past, they wouldn't drastically alter the future. You know how Stephen Hawking said, "The best evidence we have that time travel is not possible and never will be is that we have not been invaded by hordes of tourists from the future." But what if these tourists come to our time, but they do it secretly? You may even have met one of them. Let's see the most famous time travelers. Meet Orin. He's a cyborg who came to us from the year 2050 to stop the coming end of the world. In 2020, he appeared on a TV show where he said the whole world was inside the Matrix. Then he hit the headlines and gave an interview to a popular YouTube channel. As proof that he's a cyborg, he demonstrated his robotic voice, which can be made in a simple computer program. He also called himself We because he declared himself a collective consciousness that had come to save humanity. Orin became famous for his predictions about the near future, but it turned out that many experts had already announced these forecasts earlier. He also said that a huge corporation was suppressing humanity, and we were inside a complex computer simulation. If we don't improve or care for each other and nature, the end will begin in 2050. Orin no longer appears on major shows, but he has a small fan base of people who love all sorts of fantastic theories. Another time traveler is Adam Archin, who came to us from 2045. There was an interview with him on YouTube where he shared some details about the future of the US, after which the video went viral and hit the lines in many newspapers. Archin reported that the last official president of the country would be the daughter of Martin Luther King III, and she would become the greatest US president in history. Another exciting event that Archin announced is supposed to happen in 2028. He said that people would learn about the existence of extraterrestrial civilizations. He added that these creatures wouldn't come from outer space. The traveler also noted that the world would switch to a single digital currency and all cash would disappear. Of course, no one believed him, so the experts conducted a lie detector test. And Adam Archin successfully passed it. He said that he had a chip in his hand to facilitate time travel. An extraterrestrial civilization would arrive on Earth in 2028, and in 2045, people would be closer to robots. The lie detector didn't state that Archin was lying, but this doesn't mean he told the truth, since the device can be deceived with the help of special training. In any case, in 2028, we will find out whether Archin was right or not. All these time travelers arrive in the past and, for some reason, don't use knowledge from the future. What would you do if you could go back 50 years? Perhaps you would invest money in shares of some young company that will become a big, expensive corporation. In that case, everyone would believe that you really came from the past. And by the way, one guy did it. He invested $800 in the stock exchange and made $350 million out of it. This guy's name was Andrew Carlson, and he hit a big jackpot in 2003. However, he didn't manage to enjoy a rich life because the FBI came for him. Andrew sold some stocks and bought others, and did this very successfully. Thus, in a few months, he became a millionaire. The Securities Commission couldn't believe in such coincidences, so it called the FBI. During the interrogation, everyone was sure Andrew would begin to justify himself and say he was lucky. But instead, he calmly replied that he came from the year 2256 with the help of a time machine. Of course, no one took it seriously. But when the FBI started looking for information about this man, they found nothing. Andrew Carlson had no documents. He was not in any database. He just appeared out of nowhere and started making a lot of money. He was interrogated for about 4 hours, and he behaved pretty calmly. It seemed as if he was telling the truth. However, he didn't tell them the time machine's location. When the press found out about this man, he immediately became a celebrity. Well-known news sites began to write about Andrew Carlson. Articles have appeared in Japan, Australia, Germany, the UK, and other countries. And of course, journalists started calling the FBI to find out more details about this guy. And the FBI told them that the whole story was fiction and that there was no Andrew Carlson. Information about him appeared on an internet resource known for its fake news. At some point, the article about the time traveler somehow got into Yahoo, where it went viral. So, as we see, all statements about time travelers are either fiction or a lie. Conversations about such travels appeared thanks to fantastic films and books. Pop culture has greatly influenced this fantastic concept and created several theories claiming that time travel is real. And some people believe that, especially those who are far from science. But what do real scientists think about this? Are such trips really possible? Let's try to find out. Scientists say yes, time travel is real because we're now traveling in time. Time is moving forward and we're moving with it. We call it a journey. But if we need to get into the future or go back to the past, everything is much more complicated here. Remember Einstein's little theory of relativity? It says that time moves relative to the observer and has no constant value. To understand better, here's a simple example. 10 hairs on your head. Is it a lot or a little? 10 hairs in a bowl of soup. Is that a lot or a little? Everything is relative and depends on the conditions. The same thing happens with time and space. If we move at a tremendous speed, close to the speed of light, then time slows down for us. The perception of time becomes different for a person who's running and for one who's standing still. If we're near some heavy object, let's say 1,000 times heavier than the sun, then the time next to this object also slows down, thanks to its strong gravity. In this sense, time travel is possible. If you're an old person and meet your friend as young as he was 50 years ago, "Why are you so young?" "Oh, I've been flying in space at a tremendous speed all this time, that's all." But this doesn't mean that this friend just sat on the ship for 50 years and didn't age. No, time was different for him. 10 years for you on Earth is a long period of time, but for him, these 10 years passed like half an hour. Gravity and speed bend time. For this reason, astronaut Scott Kelly, who spent a year and a half in orbit, became 5 milliseconds younger than his twin brother after coming to Earth. All this time Scott spent inside the ship flying in orbit at high speed, and he was also further away from the gravitational center of the planet. So, time was slower for him by 5 milliseconds than for his brother. Objectively, time always runs at the same speed, but its speed changes inside the perceptions of different observers under different conditions. That's what the theory of relativity is about. But what about jumping into the future or the past, like in movies? Wormholes will help you with this. This is something like tunnels that pass through space and time and can connect different time segments in different places in the universe. They are like cheat codes that can break the laws of the universe. Wormholes are elusive, have different sizes, are unpredictable, appear in space, and vanish. But their main problem is that wormholes only exist in theory and sci-fi and have never been noticed in our universe by scientists.
Now, did you know that there's an astronomical object in which space and time actually swap places? How does that work? And what exactly does swapping space and time mean? Well, let's figure it out. Imagine that you're on a spacecraft. The vehicle can only move straight. Your path leads to some inevitable point, and you have no idea what lies ahead. You can only hope that it won't be too bad. Meanwhile, everything around you is complete madness. A chaotic collage of many historical events. What do you see? Ancient humans and dinosaurs? The birth of the universe? Future? Who knows? That's what the universe would look like if we swapped time and space. And theoretically, this is what you would see if you fell into a black hole and somehow were able to survive. But how is something like this even possible? First of all, let's discuss time and space. Imagine drawing a light bulb on a sheet of paper. Then grab one more sheet and draw how it lit up. Right now, it's just a small circle of light. Another sheet, the circle of light is growing. It gets bigger and bigger in size until finally it turns into a giant circle. In real life, the bulb lights up in the blink of an eye. That's because the speed of light is the fastest in the universe. But here, on our drawings, we capture the propagation of light frame by frame. We see how over time the light has grown from a small dot to a large circle. But if you connect these circles, doesn't it remind you of some shape? For example, a cone? Yes, exactly. This is called a light cone, and time is the central axis of this cone. Why? Because light turns from a small dot into a large circle over time. To remember it, let's draw a time vector, an arrow inside the cone. It goes from the past to the future. Meanwhile, the circles are space. In space, we can move however we want, in any direction. We can move up or down, in zigzags, and so on. But no matter what zigzags we draw along the timeline, we're always moving forward. We can't turn back in time, and we can't stop it. This helps us define time and space. Time is the direction in which the light cone is oriented. This is the direction where all our paths lead, and where our future inevitably lies. And space is the whole variety of directions perpendicular to the timeline. This is a straightforward graph. If it could be applied to the entire universe, then time would flow the same everywhere. However, if you've watched at least some popular sci-fi movies, you know that this isn't the case. In reality, time can be crazy. For example, if you're chilling near a black hole, what will be 2 hours for you may turn out to be 20 years for your friend on Earth. But why? Well, take a deep breath. Now, gravity comes into play. Oh, I know about gravity. It's that thing that helps me to stand on the ground, you may think. But it's much, much more complicated than that. Gravity is one of the basic physical forces in our world, and it's incredibly powerful. In fact, she's such a girl boss that she can distort space and time. She can literally influence the speed of time like an almighty wizard. How? Well, let's take something slightly bigger than a light bulb. For example, a supernova. Somewhere in the universe, a star has just made a boom. How do we know about it? Well, nothing in the universe, no sound, no radio waves, nothing, travels faster than light. So we'll know about the birth of a supernova only when we see it. And this will happen only when its light cone grows enough and reaches our planet. So the light cone grows and grows. So far, everything is fine. And finally, it reaches our planet. But there's a catch. You see, our planet is very massive, and it has pretty strong gravity. What happens then? Gravity changes the direction of the light cone. It begins to attract the cone to the center of our planet, and with it, it also attracts our arrow of time. That means it slows the time down, and the closer the light cone is to us, the more the arrow bends and the slower time goes. What does it mean? Well, for example, the fact that the watch on your ankle will lag behind the watch on your wrist, that your head is aging faster than your legs, and that astronauts in Earth's orbit age a little slower than people on Earth. This is what scientists call general relativity. Right. But how does this relate to our topic? How can we understand what will happen if we swap space and time? Don't worry, we're almost there. Now, imagine a cosmic body with incredibly strong gravity. It bends time and space so much that it feels like they swap. This is a black hole, A black hole attracts absolutely everything to its center. No stars, planets, no light can escape from there. Let's say our light cone is approaching it. First, as usual, time begins to bend toward the center of the black hole, attracted by its gravity. But the gravity is very strong, so it bends more and more, and time goes slower and slower the closer you're to the center. In the end, the light cone crosses the boundary of the black hole, the so-called event horizon. At this point, it gets so distorted that now it's literally pointing downwards. We can say that time has changed its direction. Time is pointing downwards. What kind of nonsense is that, you may ask? It'll be easier to explain in a real example. Imagine you're a crazy astronaut who decided to jump into a black hole, and there's an observer in the spaceship who watches you doing this for some reason. At first, for you, nothing changes. You look at your watch, you see that 5 minutes have passed, and everything's okay. But for the observer, first of all, you'll fall for a very long time. The observer has been sitting there for 50 years, and you're still falling, all because your time has slowed down. Secondly, since space is also distorted near the black hole, the observer will see how you'll begin to stretch like spaghetti. This is a scientific term, by the way. It's called spaghettification. And then you finally cross the event horizon. The observer doesn't see you anymore. Light cannot escape from a black hole, so your image won't reach the observer even if you're still inside. And what about you? What if you somehow survived? Remember, the time arrow is pointing to the center of the black hole. What does it mean? It means that now, the center of the black hole is your future. It isn't a place, it's a fate that you can't change. And wherever you came from, as well as the rest of the universe, no longer exists for you. Because now, it's not a place, but an event from the past. And since you can't turn back time, you'll never be able to come back. But what is around you? Complete chaos. The rays of light now move in all directions, forward, backward, and so on. The rays depicting the events of the past, the future, the present, all this is moving around you. In reality, space and time didn't swap places, but it feels like they did. Because in space, you can now only move forward, as if along a straight line. And time, reflected in the light rays, surrounds you everywhere and moves in all possible directions. And here we go back to the beginning. This horrifying example helps us imagine what it would feel like if time and space got reversed. Of course, all this is just theories and guesses. The very idea that we're moving in some one direction, the one we haven't chosen, and there's complete time chaos around, sounds quite frightening. And yet, it would be a very interesting experience. Sounds dangerous. Why don't you go first?
Your alarm goes off and you open your eyes, groaning. Wait, why is it so dark? Is it still night? Your watch says otherwise. You come up to the window and see people running around in panic. Apparently, the sun has disappeared. Interestingly, people only realize it 8.5 minutes after it had happened. That's how much time sunlight needs to reach our planet. So Earth kept orbiting the recently vanished star, and people had no clue. And then the last rays of the sun reached us. What would happen to Earth, the Moon, and other planets of the solar system if the sun was to disappear into thin air? And would humans survive this catastrophe? Now, the sun is a giant light bulb supplying energy to the entire solar system. Not only our planet, but all the other celestial bodies in our star system are locked in elliptical orbits around the sun. In other words, the sun is the ruler of our world, keeping everything in balance. You see, every planet is constantly falling towards the sun because of the star's immense gravity. But there's also a lot of sideways force, aka centrifugal force, that moves the planets away. These forces are perfectly balanced at the moment, but everything would go downhill with the disappearance of the sun. The planets would still continue their forward motion and leave the borders of the solar system. Keep in mind, that Earth revolves around the Sun at a mind-boggling speed of 67,000 miles per hour. If there was no more gravitational pull from the Sun, Earth would immediately shoot out of its orbit, and its speed wouldn't decrease. The same would happen with all the other planets in the solar system. They would go on and on through the dark cosmos until they found another object with powerful gravity that could capture them. It might last for hundreds of years. Now let's see what would be going on our planet. Animals would likely be the first to feel the consequences of the Sun's disappearance. They would become agitated as the darkness would come way earlier than usual. Birds would become quiet, settling down for the quote-unquote night. There wouldn't be any natural light at all, even moonlight. All because there wouldn't be any more sunlight for the moon to reflect. Without sunshine, there would be no photosynthesis, so plants and trees would stop growing. Herbivore animals would soon chew their way through the remaining vegetation, and there wouldn't be any food left for them, and us. The temperatures on Earth would slowly start falling. Our planet does have a core made of molten iron covered with a mantle of molten rock, so some heat would still be filtering through the planet's crust, keeping it warm. But it wouldn't last forever. People would start burning wood and coal to fight the cold and survive, but without food, it wouldn't help much. The seas and oceans would freeze, together with all their inhabitants. In the end, the atmosphere would collapse, leaving our planet vulnerable to the harmful radiation waves roaming through space. This would make life on the frozen planet even more difficult. Most living organisms wouldn't survive these harsh conditions. Those that live beneath the surface would probably survive, warmed up by the weak heat coming from the Earth's core. As for people, we would probably have to stay in large groups, using the energy received from nuclear fusion reactors. Or the whole scenario would get much more tragic. While hurtling away into space, Earth could collide with another planet, get hit by an asteroid, or even get pulled into a black hole. Or the planet could continue traveling for thousands of years until it found another star to orbit. Now, how about we take a look at what would be happening right after the disappearance of the Sun? Uh-oh, that was very disturbing. Luckily, this is a very unlikely scenario because stars don't vanish just so. They can run out of their star fuel, that's true, but miraculous disappearances won't happen. Is it possible to put out the Sun? For example, what would happen if we poured all of the Earth's oceans on it, or even more water? Well, let's find out. The universe is a place full of mysteries. Since ancient times, scientists have been arguing about how space works, but none of us has ever doubted the existence of one thing: the Sun. The center of our solar system. It's big, bright, and immortal? Nah, not really. Actually, the Sun is just an ordinary star. It consists of 75% hydrogen, a little helium, and a pinch of other heavy elements. Gravity holds it all together. But in around 5 billion years, the life cycle of the Sun will come to an end. The hydrogen inside it will run out. Our star will begin to grow gradually, and you can't even imagine just how big it will become. And then it will start eating all the nearby planets. That's when we'll regret being so close to it. After eating us all, the star will remain a red giant for another billion years or so. And then, sooner or later, it will begin to shrink and fade, turning into a white dwarf. In the end, nothing will remain of it but a bright and colorful planetary nebula. But don't get scared. Right now, the Sun is in the middle of its life cycle. It was born about 4.5 billion years ago, and about the same amount of time remains. Fortunately, we were born during the star's best and most stable period. In other words, there's no reason to worry. So let's find one. How about speeding up the Sun's life cycle with the help of water? We'll try to collect all the water on Earth and pour it onto the Sun. First, we'll need a bucket. No, not this one. We'll need a really, really big bucket. The one that can contain around 326 million cubic miles of water. It will be equal in size to the distance from Washington to Chicago. Or if we can only find ordinary buckets, there should be around 70 quintillion of them. This is a number with 18 zeros. Okay, imagine that we magically got that many buckets. It's time to put out the sun. We splash the star with all this water and nothing? Seriously? Oh, just look at this. The sun has probably felt sorry for us and produced one little solar flare. It turns out that all water on Earth is actually just a pathetic drop for the sun. People often underestimate how much bigger the sun really is than our planet. In reality, it can fit more than 1,003,000 Earths. So yes, the sun won't go out or even get colder. It won't even notice that we've done something. But let's not give up. We really want the sun to go out for some reason. What happens if we pour just enough water on it? And how much is this enough? Remember our quintillions of buckets? Well, we actually need about 370 octillions of them. This number has 27 zeros. It's hard to even imagine, so let's just say that it's a lot of water. Now, let's splash it all over the sun again. Wow, just look at the steam! But the sun hasn't gone out again. On the contrary, it said thank you and suddenly became much bigger and brighter. What's happening? You see, the sun isn't actually a campfire. Inside bonfires, candle flames, there's a chemical combustion. When we pour water on the fire, the water absorbs the heat of the flame and cools it to such an extent that it can no longer maintain the burning reaction. It also blocks the fire's access to oxygen. Water basically stops the chemical process. But the burning of the sun isn't the same reaction. Even though we say it burns, it's not entirely true. What happens there is called nuclear fusion. It's one of the most violent and craziest reactions in the universe. There are many layers of hydrogen going deep into the sun. If you take 4 hydrogen atoms and ram them together, you're left with an atom of helium. When we talk about the sun, the process is a little more complicated. When the star tries to carry out that fusion, positive protons repel each other. It takes a lot of force and energy to somehow squeeze them together. Fortunately, there's a magical force in space. It's gravity. The sun takes up 99.8% of all the mass of the solar system. Pretty heavy, right? And all this mass is what holds the sun together with the help of an incredible gravitational force. So, gravity takes quadrillions of these little hydrogen atoms and pushes them together every second of every day. And when they collide, they release some energy. So, unlike fire, the sun doesn't need oxygen to live. It needs hydrogen. And we all know that water is H2O. It consists of hydrogen and oxygen. So this is literally fuel for the sun. It's like trying to put out a fire with gasoline. More importantly, the extra mass added by water will make the sun heavier. Now, gravity says, thank you for your help. And then it starts to collide protons with each other even faster. And thanks to this, the synthesis speeds up. Great, we've made the sun incredibly strong, and now it has eaten us, along with other nearby planets. And if we keep adding water, the sun will sooner or later collapse in on itself. It will blow off its outer layers and become a black hole. Awesome! Now it will pull inside absolutely everything around. Good job, guys. Let's press rewind because clearly our water experiment was a mistake. One small solar flare sounds much better. Alright, we're back to our usual calm sun. But it seems like there's something that we've forgotten. Well, apparently, water was critically important for life on Earth. Who would have thought? Now there's a huge amount of unmoving fish and other marine creatures lying around where the oceans used to be. Poor things. As for deep-sea creatures, they simply didn't withstand such a sharp change in pressure. Algae and corals have also dried up. Wait a minute, weren't they responsible for producing 50 to 80% of the world's oxygen? Oops, it's time to put on some oxygen masks. And how are things on dry land? I mean, now everything is just land. But you get the point. Wow, this whole place is lit, and I mean it literally. If there are no oceans, then there are no clouds or rain. Now there are forest fires everywhere. Poor animals have to escape and leave their homes. Oh my. And it's not like they'll be able to find a new home, because all plants, of course, will dry up quickly. There will be literally no place for living left on the planet. So now Earth looks like a giant desert. Great! But people have been living in deserts for thousands of years, right? Maybe they'll know what to do. They won't. After all, people in the desert also need to drink. So now there's total chaos everywhere, and survivors fight for the last drops of water. If there are any survivors at all. In fact, no matter how much they fight for resources, their fate is sealed. The ocean absorbs a huge amount of CO2 and the heat coming from the sun. They also distribute this heat throughout the planet, making it pleasant to live on. But once they're gone, the temperatures will quickly jump to 250 degrees Fahrenheit and above. But even if we forget about the high temperatures, now we have no clouds, and they helped us too, by not letting through solar radiation. So we're also under the direct impact of the sun's rays. Our last hope is icebergs. Now that everything is terribly hot, they've melted. And maybe they'll be the last hope for humanity. But that cool solar flare was definitely worth it. Silly humans.
It's becoming colder by the minute. The temperature drops below zero very quickly. And although there's no snow, the cold is becoming unbearable. Hoarfrost appears on the ground, the grass, and the trees, and ice forms on bodies of water at an incredible rate. Shivering people all over the planet raise their eyes to the sky, and their jaws drop in disbelief. The sun has become twice as small as it used to be. It now looks like a distant speck, and it won't be able to heat the Earth any longer. But the worst thing is, there's a huge blazing rock coming right at the horrified spectators from the sky, and the impact with that thing will undoubtedly do a lot of damage. Okay, let's go back to our objective reality. The Earth is exactly in the sweet spot of our solar system. It's neither too close nor too far from the sun, making the temperature on our planet not just tolerable, but rather pleasant. Scientists often call Venus, the second planet from the sun, our Earth's evil twin, because it's so hot and inhospitable that no life is possible on it. Of course, there are thick clouds in its atmosphere that rain acid, and the greenhouse gases raise the temperature on the surface to unbearable values. But even if Venus didn't have those, nothing would still be able to live there, either rise or fall respectively. A few hundred miles wouldn't make much difference. The circling of Earth around the sun is uneven anyway, and we constantly get nearer to our star or fly a bit away from it. The distance that would matter is measured in millions of miles. And yeah, just like I showed you at the beginning of this video, we'd see the sun a lot smaller than we do now if we went that far. The temperatures might not fall at the exact moment of the shift, as there would still be some warmth left. But in the following winter, our planet would probably stay cold forever. The oceans would be covered with ice, and the overall sea level would drop. And ultimately, the ice would reflect more of the sun's heat back into the atmosphere and space, not allowing the surface of our planet to get the necessary warmth. And more ice means less water vapor in the atmosphere. Water vapor captures heat too, creating clouds. So the colder it is, the less rain. The cold and the lack of rain would not let any plants survive for long. So the areas of icy and barren landscape would grow fast, leaving only the areas along the banks of rivers intact for a while. After some time, the rivers would stop running too, either frozen or dried out because of losing their sources, lakes and seas, which would, of course, freeze as well. Any life dwelling near them would disappear. Plants first, and with them, everything else, since plants produce both food and breathable air. And with that, the Earth would become a frozen wasteland. As for the giant blazing rock I mentioned, it was an asteroid coming from outer space because of the shift of our planet's orbit. Jupiter, the largest planet in our solar system, acts as a natural shield for us against space rocks. It has a huge mass, and most asteroids flinging from outer space get caught in its gravity and fall on its surface. There's no life possible on Jupiter, and its surface is gaseous, so asteroids tend to disappear in it without a trace. Still, some manage to get past Jupiter, where Mars comes into play. It also contributes to our defense by holding the asteroid belt between itself and Jupiter in place. The two planets' combined mass creates a gravitational field that doesn't allow the asteroids from the belt to fly in random directions, hitting everything in their path. If there was no Mars between us and the belt, we'd be used to meteor showers almost more than actual rains. Say the Earth has replaced Mars in its orbit, and now we're hundreds of millions of miles farther away from the Sun. The mass of the Earth is more or less similar to that of Mars, so the asteroid belt is still in its place. The temperatures will still fall though, and life will soon go extinct. But if Mars stayed where it is, and the Earth just shifted away, it would be a recipe for disaster. There's no chance the planets would orbit the Sun at the same rate because their mass is not equal. At some point, they would collide with each other. Taking their speed into account, they'd both crack and shatter, perhaps creating another asteroid belt in our solar system. It would be no more hopeful for us if the Earth decided to jump closer to the Sun. Apart from the star seeming more like a giant, pitiless blazing ball in the sky, its heat would melt the glaciers on our planet, making sea levels rise abruptly. The water would flood major parts of the continents, and more surfaces of the planet would be covered with water, which means more heat absorption. That would bring about a further rise in the temperature. Also, those large bodies of water would evaporate like crazy, releasing tons of water vapor and carbon dioxide into the atmosphere. Carbon dioxide is a greenhouse gas that absorbs heat, and so does water vapor. Together, they would trap more and more of the sun's warmth, creating thick, roiling clouds in the sky, almost like on Venus, but without the acid. And that thick blanket of clouds would also contribute to heating the surface of our planet. In the end, the entire Earth would heat up so much that life on its surface would become unbearable for most. Only the sturdiest of creatures would be able to survive temperatures so high, those that dwell in our deserts, for example. Despite the rainfall, which wouldn't cease as in the cold scenario, plants would still have difficulty adapting to the new and hot environments. The ones in the cooler regions of the planet would be the first to wilt and go. But then, plants from the moderate and finally tropical climes would also give up. And, yet again, the Earth would turn into a barren ball of rock, only this time an overheated one rather than frozen. Our planet's distance from the Sun, its tilt, its speed of rotation around its own axis, its orbit around the Sun, and even the presence of the Moon in its skies, all of that is crucial for life on Earth to exist. For instance, if the planet wasn't tilted relative to the Sun, it would be unbearably hot on the equator and impossibly cold at the poles. The seasons would also stop changing, dividing the Earth into strips of endless summer and winter. Our planet is heated up evenly from all sides, with the current tilt and rotation, like you would roast a barbecue. It turns to the Sun with one side to warm it up, while the other cools down during the night. Were there no change of night and day, we'd probably only live in some areas of our planet where constant, never-ending twilight would be. Just imagine our life without those beautiful sunrises and sunsets. Maybe we'll just let it stay as it is, okay?
You hear some noise in the street and rush up to the window to check what caused it. You look up at the sky and just stand there, speechless. The moon is giant. It looks much larger than usual, and it's both beautiful and scary. So what would your life be like if the moon moved twice as close to Earth as it is now? Unfortunately, it would be quite a catastrophic scenario. You see, the moon has a pretty strong gravitational pull on Earth's oceans. It produces 2 high tides and 2 low tides per day. But with the moon so close to us, the tides would get 8 times higher. Some regions would be completely covered with water during the day. The water would only retreat at night. Many islands and highly populated coastline territories would become uninhabited because of this. Many other regions would experience frequent devastating floods. But if you think it would be the only consequence, let me tell you this. The moon also has a tidal effect on dry land. That's why if our planet's natural satellite was to suddenly relocate, its gravitational pull would increase, making waves of energy reverberate throughout the planet. This would affect Earth's crust, triggering earthquakes and starting volcanic eruptions. Now let's leave Earth and the giant moon for a while and have a look at Jupiter's moon, Io, which is the most volcanically active world in our solar system. This volcanism comes from the push and pull from Jupiter's gravity. 2 other moons of the gas giant also have an effect on poor Io. That's why Io's surface is littered with hundreds of volcanoes. Most of them are spewing sulfurous plumes high above the surface of the moon. Our planet might face the same fate should the moon move so close to it. And that's not all. Earth's spin would start to slow down over time. Look, the moon's gravity pulls the oceans, and the resulting friction between the water and the ocean floor slows Earth's spin. Yes, Earth is slowing down even now as you're watching this video, but this process is almost imperceptible, around 1/1000th of a second per century. If the moon was twice as close to us, the rotation of our planet would slow much more, making days and nights longer. If people managed to survive unexpected earthquakes, high tides, and volcanic eruptions and got used to longer days and nights, they would get an award. Solar eclipses. These spectacular events that occur when the moon passes between the sun and Earth would happen much more frequently. Since the moon would cover a much larger area in the sky, it would pass in front of the sun more often. People on Earth would be able to see the sun's outer atmosphere, called the corona. It would shine beautifully around the silhouette of the moon. Such solar eclipses would also last much longer. But what if the moon didn't shorten the distance overnight? What if it was a much slower and much more gradual process? Then our planet's crust would shift more slowly. Tides wouldn't change so dramatically either. This would let living creatures on the planet get used to the new conditions and adjust in time. Longer days and nights would likely change the climate, and animals would have to evolve to adapt to it. Their eyes would have to change to be able to deal with brighter moonlight at night. Prey would have to learn to hide better, but predators, on the other hand, would have more advantages when hunting. But what catastrophe would have to happen to make the moon move so close to Earth? Well, it could be some massive object, like a giant asteroid passing very close to the Earth-Moon system. If the moon was in the way of this space traveler, it could take energy from Earth's satellite, which would cause the moon to spiral towards our planet.
Have you ever seen the other side of the moon? Ah, I caught you. Of course not. But maybe you've seen it in photos. In that case, have you ever wondered why the two sides look so different? Well, let me tell you. We can't see the other side of the moon. People believe this is because the moon doesn't rotate around its axis. But this is not true. The moon does rotate. It just does it at the same rate as its orbital motion. This is a particular case of tidal locking called synchronous rotation. The first time we ever saw a far side was only in 1959, all thanks to the Soviet Luna missions and later the US Apollo program. Now, when Luna 3 and other spacecraft transmitted the first far-side images, they revealed a far more cratered hemisphere that looked more like Mercury or Jupiter's moon Callisto. It looked completely different from what we were used to, and that's when we learned how meh the other side is. No, seriously, just look at it. The near side can boast its thinner and smoother crust. These beautiful dark splotches are called lunar mare, the last remnants of ancient lava flows. And when I say ancient, I mean it. They're more than 3 billion years old. Meanwhile, the far side crust is thicker and crater-pocked. The lava flows had almost no effect on these impact craters. It's also devoid of any large-scale mare. Low-key looks like dried white cheese. To be honest, don't you agree that the nearby side is much more beautiful? Write your thoughts in the comments. So, only 50 years ago, we learned something about the apparent differences. But then the scientists discovered something weird. Both sides are different, even in the geochemical composition. And not only in this, our side was thinner than the far side by several miles. But where did such significant differences come from on an ordinary floating stone ball? For scientists, this was a mystery. They started coming up with a lot of theories. The melted moon theory was the main one for a while. It said that it was the Earth's fault that our moon looks like this. This happened several billion years ago. The moon was born because of a collision. One day, an object about the size of Mars crashed into the Earth. At that moment, a piece broke off from it, which later became the moon. However, this piece was somewhere 15 times closer to Earth than it is now. Some scientists created pictures of the so-called early moon. Unlike our cute little white ball, the early moon was a strange-looking, boiling scarlet ball. That piece didn't leave us after the separation. It became tidally locked very soon after. The Earth after the collision was still an incandescent nightmare, full of fire and lava. It was boiling at a temperature of 4,500 degrees Fahrenheit. And since the moon has always been turned toward us with one side, this side has melted down a little. This would explain why the moon's surface, the so-called mantle, is thinner on the near side than on the far side. During the boiling of the Earth, certain elements evaporated from it. They then settled on the moon. This would explain the difference in geochemical composition between the two sides. But there was a plot hole in this theory. If that's what happened, then where did rare foreign chemical elements come from, such as unusual isotopes of phosphorus, potassium, or tungsten? The nearby site is full of them, and they couldn't have come from the Earth. There were also other theories. Another one said that initially we had two teeny-tiny moons. Later they merged into a big one, hence the difference in their composition. But this theory sounds a bit crazy, and it has a plot hole too. For example, the transition between the two sides is way too soft. If our moon was actually two tiny moons, this transition would be more abrupt. So scientists were kind of at a loss on this one. But recently, they finally figured out what really happened to the moon, all thanks to NASA's Grail orbiters. They spent over a year whizzing around the moon, mapping it out, and studying its composition. Using this data, scientists have created around 360 computer simulations. They contain different impacting objects of many sizes, traveling at different speeds. Scientists were comparing the results with our current moon. They tried to determine which result was the closest to what we have today. And so, they finally solved this 50-year-old mystery. The answer lies in a collision with a dwarf planet. This collision occurred 4.3 billion years ago. This huge object was slightly larger than Ceres. For those who don't know, Ceres is one of the dwarf planets of our solar system. Its diameter is 580 miles. You could say that one France or one Germany would fit into it. So, this giant object crashed into the moon, somewhere near the South Pole. This collision was so strong that it changed the image of the moon forever. It left a trail of 3,500 miles behind. It would take you 14 hours by plane to fly that distance. This crater covered the entire near side of the moon. It caused damage to the moon's mantle. It also created a so-called South Pole Aitken Base, or SPA basin. This is an impact crater and has a diameter of 1,600 miles, which is like adding one UK plus one Germany. It's important, though. The formation of this basin was a defining event in the history of the moon, and it's the second largest impact crater in the solar system. The collision also caused a powerful hot wave to spread across the moon. This wave scattered over the remnants of those rare warm minerals scientists found on the nearby side. That's how our beautiful side became home to something called Procellarum creep terrain, or PKT for short. This is basically a compositional anomaly, a concentration of potassium, phosphorus, and other rare elements like thorium. You can say that those minerals are a gift to us from deep space. Anyway, there were many, and I mean many, collisions in the Moon's history. All of them only deepened this already large crater. That's why the mantle on the near side was getting thinner and thinner with the years. Also, our gifted minerals gave off a lot of heat, so the mantle has melted a little bit more and more. Oops, this accidentally caused the Moon's volcanoes to wake up. Volcanic activity has increased on the near side. Intense lava flows filled the old empty craters. Ta-da! And this is how the beautiful lunar mare was born. That's about how it all happened. All this information was found thanks to the researchers from Brown, Purdue, Stanford Universities, and NASA's JPL. The research was published by the Journal of Geophysical Research, Planets, so you can read about it in more detail if you're interested. There are still many things we need to learn about the Moon. The highest priority is the return mission from the South Pole, the Aitken Basin. Samples brought from there will be used to determine the age of the Moon, its history, and the nature of the crust and mantle more accurately. Another critical target is the Moscovians. This is the name of a large lava plain on the far side of the Moon. Studying it will help us better understand the difference between the two sides, as well as tell us how the other side was formed. All this knowledge is significant for understanding the history of the Moon, but it's also handy for space exploration in general. Scientists use the Moon as a reference point to determine the age of other planets and entire worlds in space. The Moon helps us determine the chronology of the life of the whole solar system. So stay tuned for new exciting research and discoveries. You're strapped in your seat in the vast open space with Earth behind you getting smaller and smaller. All around you are toggles and controls to keep the spacecraft intact. You and 2 other crew members are working hard at those controls. Out the window, you see some meteorites flying by and stars and planets out in the distance. You're about to be one of the first people to land on the Moon after years of research and testing. You have to consider all the steps perfectly. Otherwise, you could face many complications, like crashing into a flying asteroid, or even being left in the vacuum of space without any way of getting on track. Research shows that around 1/3 of all moon landings faced many problems. Launching towards the Moon requires a special rocket traveling at more than 25,000 miles per hour. And once in lunar orbit, the spacecraft can detach itself from the rocket and navigate its way to the surface of the Moon and land. Sounds simple, right? Well, figuring out the math to land was the reason landing a human on the Moon used to seem like a ridiculous idea. But scientists were able to pull it off by studying and observing the flight of helicopters. Unlike an airplane that needs velocity to take off, the large propellers on a helicopter give it a good push to fly around. It basically has to twirl with enough force to lift its own weight from the ground. With that in mind, we need to consider the gravitational force pulling everything down. On Earth, the force of gravity is 32 feet per second squared. On the Moon, it's only 5 feet per second squared. So we got landing on Earth figured out for the most part, but what about landing on a surface that barely assists you in that? There had to be 3 steps, doing all the research and math needed for calculating the proper conditions, using a test vehicle to practice in, and using a flight simulator to imitate the conditions of the Moon's atmosphere. Choppers weren't really good references for landing, since gravity is doing most of the work, and the spacecraft looks nothing like a helicopter. They needed to simulate a spaceship of only 5/6 the weight of it. Since the gravitational pull on the Moon is weaker than on Earth, navigating it under these conditions is vital for when the real thing comes. The scientists of NASA decided to get a crane hanger to lift the spacecraft with cables while simulating the flight and landing. kind of like stunt actors in a movie with cables attached to them for action fight scenes. But it still wasn't enough to determine if you could actually land properly on the moon without the safety cables to help you. They needed proper freedom. So it was back to the drawing board. They were about to throw in the towel until they came up with a brilliant idea to simulate the landing conditions on the moon by installing a sort of detachable jet fan into the bottom of the spacecraft to keep consistent thrust upwards. By doing this, they were able to create a scenario where the craft would be 5/6 of its weight on Earth and without the safety cables to hold it. But after many trials and errors, the only way to see if landing on the moon was possible was by actually doing it. So, being so far away from Earth, you and your team see the moon out your window. It's a lot bigger than it looks from Earth. Its surface fills up the entire window. But landing won't be a piece of cake. The spaceship has to orbit around the moon to determine the best time to land. And don't worry, that's why you have a team for that. It can take more than 24 hours to know when and where the perfect place to land is after performing various tests and measurements. And once you get the best calculations, the actual spaceship detaches from the orbiting one and makes its way downwards. This is where the helicopter physics come into play. A helicopter needs to tilt at least 5 degrees to move forward after ascending from the ground. Same for going backwards. But that's because we have gravity to assist it. Up above the moon, soaring through the vacuum of space, the ship would need to tilt at least 30 to 40 degrees to move forward. As soon as the ship reached a nice spot for landing, it would go back to 90 degrees and slowly land on the surface. As you get closer, you can see the moon's surface just a few feet away. This is the tricky part, but it's a success. The team back on Earth couldn't be happier. The crew members are also thrilled about what you've achieved. You put on your spacesuit and gear and climb down the ladder. You leave your first footprint on the moon and look out at the distance ahead of you. The Earth is just a little blue dot far away. You're able to bounce around in the near-zero gravity. Now, that's what I call moonwalking. After spending much time on the moon, it's time to head back. Neil Armstrong, the first man to step on the moon, spent only about 2.5 hours on its surface before returning. But, oh no, you forgot the keys inside the ship and now you're stranded. Nah, just kidding. Although it would have made a good plot twist. You get back and launch the spacecraft back into orbit to reunite with the other ship above you. And once you've reattached, you exit the moon's orbit and head back to Earth. By sending humans to the moon consistently, the next big step can be achieved by landing on Mars. The famous exploration rover Curiosity traveled around the surface of Mars and gathered information needed for humans to land there. And NASA is aiming to have the first humans up there after 2030. The journey will be hundreds of times harder than the one towards the moon, but many scientific questions will be answered once it happens. Humans may be able to gather some of the natural resources there and even build outposts and colonies. There are endless possibilities as well as challenges. The journey from the Earth to the Moon is around 250,000 miles. Mars is around 35 million miles away. There could be a possibility of a new human outpost station on Mars, building a new society of scientists and engineers to make the most out of the conditions. It would be completely self-sufficient, providing proper ways for farming and agriculture. And by having humans on Mars for so long, scientists can properly understand the planet. But to understand how the human body responds to deep space environment, we'd have to have a lot of practice before getting that ticket to Mars. The closest experience of having a colony in the middle of nowhere is the Amundsen Scott Station on the South Pole. It's designed to withstand all the harsh conditions of the freezing dry cold. Being at the bottom of the world can be pretty stressful without proper practice. The journey may not be as far as Mars or the Moon, but being on the South Pole is like arriving on a whole new planet. The station itself is equipped to provide the proper conditions everyone needs to be comfortable. Besides the strong heating system, the station has a recreational room for sports and music, a library, a lounge, and even a greenhouse to grow all the right veggies and fruits. In fact, the greenhouse is the only way you'd get to feel like you're in a rainforest. And even before applying there, you'd have to get screened to see if you can handle the isolation for months. Not that you'd be completely alone, but still away from civilization. Antarctica's whole population consists of scientists and engineers, and you need to be examined by a doctor to determine if you're physically fit to stay there. The station is built there for scientists to study space and things related to geology. Being in the biggest desert in the world can take its toll on you. When leaving the station, you have to wear at least 3 layers of gloves and extremely thick sweaters and jackets to withstand the cold. They even compared stepping on the South Pole to walking on the moon.
Time runs like a river. It has direction, always advancing. It has a certain duration, periods between events you can measure. Time feels real, always there, unstoppable, moving forward. But what if I told you that time might not exist? Some physicists and philosophers claim that there might be no such concept as time, and we should take this possibility of the non-existence of time seriously. You see, recently physics has been in crisis. For the past century or so, 2 extremely successful physical theories have been used to explain the universe. Those are the theory of general relativity and quantum mechanics. Quantum mechanics describes how things work in the super tiny world of particles and their interactions. As for general relativity, it provides an outlook on the bigger picture, for example, gravity or how objects move in space. And even though both of these theories seem to be working really well, they are believed to conflict with one another. That's why some scientists think that they need to be replaced with a new, more general theory, like quantum gravity. This idea might be able to explain how gravity works at the miniature scale of particles. Apparently, it's incredibly difficult to produce the theory of quantum gravity, but it might be possible to do it with the help of string theory. It replaces particles with strings, vibrating in 11 dimensions. But there's one problem. Even though string theories do provide several models describing the universe, they don't make any clear predictions that can be tested by experiments to understand which model is the correct one. There's one more idea known as loop quantum gravity. According to it, the fabric of space and time is made of super tiny chunks, loops. But the most remarkable aspect of this theory is that it completely eliminates the concept of time. Now suppose this idea turns out to be correct. Will it mean that time doesn't exist? Well, the answer is kinda complicated. Everything depends on what the word exist means. A philosophy professor from Cambridge University claims that the 3 basic properties of time, a present moment that is special, the flow of time, and its direction, come from our mental states and not from the physical world. So we sense this arrow of time because our minds add a certain subjective ingredient to reality. At the same time, Einstein's theory of relativity supports the idea of the block universe, a 4-dimensional space-time structure where time is like space. It has its own coordinates in space-time. Time is tenseless there. Thus, the future and past are as real as the present. Does it mean we're being fooled by our human perspectives? Is the feeling that time passes and has a certain direction false? Well, we can imagine our world as a 3-dimensional place where stuff happens gradually over time. Or it might be a 4-dimensional space where nothing actually happens because nothing changes. It's all here at the same time, past, present, and future. The main idea of relativity is that there's no absolute space and no absolute time. Everything is relative. Trying to think about time in the context of the universe, you realize that you need to isolate part of it and call it, let's say, your watch. And time is basically the relationship between some parts of the universe and that thing you called your watch. Another scientist says that time is just a collection of snapshots describing our reality while continuously changing one into another. Here, you hit play. Here, you're blinking while watching this video. And here, you're taking a sip of your coffee. Without these changes, there wouldn't be any notion of time. The changes are real, but time is not. Our brain sees these changes and constructs a sense of time, believing that it's flowing. What do you think? Is time just a social construct, or does it really exist?
Oh boy, you can't stop seeing images of funny pandas on your final exam sheet. All those late-night YouTube videos hit you hard, huh? You scribble down some words, hoping that something makes sense. You look at your watch and realize you've got only 10 minutes to finish. Panic mode is officially on, but no one knows your watch has a pinch of magic in it. You click the stop button on your watch and relax. Don't worry, no one will turn to dust and half the universe won't disappear. You simply freeze everything in time except yourself. With this ability, you can stop the time for 1 minute a day. So after freezing time, you get to one of your classmates, take a picture of the assignment, and head back to your seat. You unfreeze the time and write down the proper answer. Whew! At least you can guarantee a passing grade. I'm Steve from Legal. Want to make sure you know that Brightside does not condone cheating on a test. Okay, carry on. You walk out of the classroom with a large smile on your face. You check your watch and it says you spent 10 seconds of time freezing. 50 seconds left. After that exam, you go and grab something to eat. You're at the traffic light waiting to cross the street. Hey, there's a girl talking on the phone and a car is speeding up to her. Everyone sees it, but nobody can do anything, and the car is only a few feet away from her. You click the stop button and everything freezes again. You run up to that girl and move her as fast as you can. Then you run back to where you were standing and click the button again to unfreeze time. Everyone is confused, but at least the girl's safe now. The whole mission took you another 10 seconds. 40 seconds left. You enter the coffee shop to grab a quick bite. As soon as you get your coffee, you turn around and lose balance. Your drink is falling down and about to spill. You click the button instinctively, and the drink is now literally hanging in the air. You collect all the droplets and put them back in the cup and click the button again. You just saved yourself $5 and a dry cleaner's trip. You realize you spent 15 seconds saving your drink. 25 seconds left for today. As you're walking to the bin to throw away the cup, someone bumps into you. The buckle unfastens and the watch smashes onto the ground. You pick it up and see a scratch on the display, plus some parts came off. You gather the parts, trying to fix it. As you're doing so, you see a fly next to you and shoo it off. Strangely, it doesn't even flinch. You look around and see everyone frozen in time. The person who bumped into you is still in mid-motion. The pigeons eating breadcrumbs are frozen too. So are the cars and people. Since the watch got damaged, it reversed the power. Everything is on pause, and now you've only got 25 seconds of regular time. If you waste it all, you'll be frozen in time forever. At first, you try your best to fix it, but don't know what to do. You take out your phone to browse some tutorial on how to fix a watch, but it won't load. You keep refreshing, but nothing happens. The internet can only work in real time, and 25 seconds aren't enough for anything. There's only one place now where you can learn how to fix watches in this situation: a library. You'll have to read about it and learn from scratch. You rush to the closest library, which is at the campus. Turns out there are only a few books on how to repair watches, but they have zero info you need. You find a bike and pedal all the way across to the public library. It took you 4 hours to get there. Once you've arrived, you look at endless bookshelves. You could easily switch back to real time and ask the librarian where to find what you need, but then it might take longer than you have left. There are way more books than you expected. You pedal back home and grab some stuff to sleep and eat. It's going to be a long day. When you're back, you grab a few large books that seem to have the answer. No social media can distract you, since the internet doesn't even work. The time passed and you finally finished 2 large mechanics volumes. But there's just one problem. You can't find volume 3. Your only chance is to turn on time to do a quick internet search on where it is. You can't download an ebook since it will take much time and it's impossible to print in frozen time. You click the button and time resumes. Everyone looks confused about a mattress and food leftovers all over the library floor. But you do a quick internet search and find out that you can order the book now and receive it the next day. Yeah, right. It turns out the closest book is in a library on the West Coast. Bad news, you're in New York. And what makes it worse is that the only source was updated years ago. The book may not even be there. You freeze time again. It took you 10 seconds to get all the needed information. You have no choice but to go on a road trip that will take around half a year by bike. No other vehicle is available to you. You find the best bike and gear, pack up some provisions, and leave the town. You travel through the mountains, swamps, and dry lands. You bike through frozen waterfalls and cut across heavy storms, frozen in time. You find indoor places to sleep, since time is frozen during the day. But you actually took your time getting there and lengthened your trip to see all the sights around the country. You spent a week at the Grand Canyon and a month in Yellowstone. You went up to bears and wolves so you can actually see the details of their muzzles. You even decided to pedal all the way to Mexico to check out the amazing scenes and landscapes around. You visited all the cities and towns without worrying about money or a proper place to stay. Steve from Legal again. Brightside does not condone using stuff without paying for it. Remember, this is a fantasy trip. Okay, continue. After covering all of Mexico, you continue all the way down through Central America, where you got to witness even more amazing sights and landmarks. Hey, you've already gone this far, why not continue pedaling down to South America? You can even visit your friend in Argentina. I mean, he wouldn't know you're there, but it would be nice to pay him a little visit. After sunbathing in Brazil and mountain climbing in Bolivia, you end up at the southernmost point in South America and admire the journey you took. Right across the ocean is Antarctica. It's impossible to get a boat and sail there, so you decide it's time to get back to business. According to your calculations, it took you about 4 years to complete this journey. But you finally reach the library. You take out some water to drink, but accidentally drop the watch on the ground and resume time. Everyone is in motion. Cars are honking their horns, dogs are barking, people are screaming and shouting at each other. You haven't heard a human voice in such a long time. Some people are staring at you. You're overwhelmed by all the energy around you, but suddenly wake up from it. You fumble trying to find the watch. Here it is. You stop the time. Only 3 seconds left. You spend what seems to be another month in that large library trying to find the third volume. You've got no more time to do another internet search with those 3 seconds. After you finally found it, you spend 2 more months figuring out how to fix your watch. When you're done, all you have to do is click the button to bring everything back to normal. But you decide to pedal all the way back home. You clean up all the mess in the library and go back to the coffee shop where it all started. You even return the bike you borrowed. This is it. 3 seconds to see if all that work was for nothing. You click the button and watch time move on. You look at your watch. 3, 2, 1. Whew! Everything is back to normal. You go back home and lock up that watch in your drawer, never to look at it again. Until next time.
15,000 years after the construction of the first space colony, planet Kepler 452b, 1,400 light-years from old Earth. Hello, first-year students. We're glad to welcome you to the Intergalactic University. Endless space is now home for us humans, but thousands of years ago, we used to live on just one planet we now call Old Earth. Yes, I understand it's difficult to believe. Today, it's one huge nature reserve. Mammoths and stegosaurs walk on its surface, and pterodactyls fly in its skies. It turned out to be easier to recreate animals that roamed it millions of years ago than to understand how our ancestors lived. The Great Cataclysm made them abandon the planet in a hurry, leaving much of its legacy behind. And now, we're studying it anew. But our excavations leave more questions than answers. Skyscrapers, highways, shopping centers, coffee shops. Everything is buried under sand and soil. Rust has eaten away the metal, and time turns concrete into dust. Even the Hoover Dam and the Three Gorges Dam in China have crumbled. The colossal structures turned into heaps of stones. The remaining buildings have become overgrown with plants and turned into a home for millions of living creatures. But there's good news as well. Faces carved into Mount Rushmore are still visible. The mountain is granite, and this rock is one of the hardest on old Earth. For over 15,000 years, the faces of U.S. presidents have deteriorated by only 2 inches. The monument will stand for millions of years. And the latest expedition to the Sahara Desert managed to dig out the Great Pyramid from the sand. Now any tourist can buy a ticket and look at that wonder, which even Earthlings considered very old. Surprisingly, ruins and crumbling walls of medieval castles in Europe have survived. They're built of massive stones and without metal fittings, which expand and destroy the stone when rusting. Our ancestors left behind a huge amount of garbage. Empty bottles, plastic packaging, wrappers. All this helps scientists to recreate the consumption patterns of people of the past. Thanks to this, we know for sure that in the 2000s, almost 8 billion people ate mostly chips, chocolate bars, and pizza. And they rarely drank ordinary water. They loved coffee, though. 60% of Earthlings lived on the internet for 7 hours a day. 2 billion websites worked 24/7. At first, information was stored on hard disks, flash drives, and compact disks. But this kind of storage went obsolete after a couple of years. The cloud took their place. It was an online storage with servers connected to the global network. They recorded the entire life of Earth's civilization and were stored in data centers. In space, the Earth's internet didn't work well. Apparently, huge distances and lack of technical knowledge did their job. Imagine that a Pluto resident wants to know the difference between margarita and calzone pizzas. They click the link and wait for a couple of hours for it to open. If the dough's already in the oven, no good. Each colony organized its own internet by sending satellites to orbit their planets. It took time to connect thousands of colonies into the intergalactic web we now know as Uninet. When the cataclysm struck, people had to escape, leaving their planet to its fate. Electricity went out, no one maintained the servers and data centers, and lots of info about their civilization was lost. We've scanned miles deep into the Earth and found many interesting artifacts. Students, I invite you to look at this amazing thing. The Earthlings called it a camera. People took pictures of their food, morning runs, and new shoes on it. One thing our scientists couldn't comprehend, though, is that ancient people used to communicate with its help too. One of the main mysteries of the past are the dishes of different sizes. Archaeologists find them in almost every home. They bear these names: Buddy, Cosmo, Rex, Princess. We know these were the things from which dogs and cats ate, but we don't know why people pampered these animals so much. For example, archaeologists recently unearthed a beauty salon for poodles in San Francisco. I also love my dragon from the jungles of Galactic 832c, but I don't perm its fur and manicure its claws. And this is my favorite artifact, a book. There's nothing more valuable in the universe. There's only one sample in my antiques collection. It's a cooking recipes anthology. I paid a fortune for it. The ruins of museums are treasures for archaeologists and all the new humanity. These buildings collapsed a long time ago and now look like ordinary hills, overgrown with trees and grass. Museums are like pearls in the ocean. They lie at the bottom and wait to be fished from their shells. And sometimes, archaeologists manage that. Books, paintings, documents, and clothes have mostly turned to dust. But we can enjoy the statues that were carved out of marble by masters of ancient Greece and Rome. On the walls of caves around the world, there are drawings of animals and handprints of the first people. They didn't know how to read, drive a car, or fly a spaceship, but their paintings have survived. It's incredible. Over thousands of years, time has eaten up huge dams, cities with skyscrapers and bridges, and the palm of an ancient human still adorns the cold and rough wall of a cave. Space archaeology is becoming more and more popular. Thousands of tons of space debris fly around old Earth. The real sensation is the discovery of the Voyager 1 probe. Earthlings sent it into space at the very beginning of their development. I see your condescending smiles. Today, such a device can be assembled by any first-year student from spare parts in their parents' garage. But, dear students, let's not laugh at our ancestors. They tried their best. Voyager isn't a simple satellite. The device can be compared to a message in a bottle thrown into the sea. And the cosmic sea is millions of times larger than the Pacific Ocean of old Earth. Engineers of the past left a time capsule with a message in the probe. It contains photographs of people and the nature of the planet, as well as scientific information about the Earth. 90 minutes of recorded music are of particular interest. This is a real gift from our ancestors to us, to the people of space. Radio signals that humankind sent into space have also survived. We've tracked them. Radio broadcasts, phone conversations, even music charts continue their journey through space. Millions of years later, they'll weaken and leave behind only an electromagnetic echo. In 2020, there were 1.4 billion cars on old Earth. Unbelievable! But they moved along asphalted roads on rubber tires, not in the air. When humans flew into space, they left their vehicles on the planet. Within just a couple hundred years, the cars went completely bust and turned into piles of metal, plastic, and rubber. One that survived for millennia was the Lunar roving vehicle. There's no air, no water, and no earthquakes on the moon. Anything that comes here becomes kind of suspended in time, and that's what happened to the rover. Archaeologists have found a lot of other whole and crashed spacecraft on the moon. These devices are priceless artifacts in the Museum of Primitive Earth Technology. In the Svalbard archipelago in the Arctic Ocean, scientists have unearthed the Global Seed Vault. Earthlings built it in 2008. It became a real sensation. The huge silo contained 4.5 million samples of 500 seeds each. Billions of seeds have helped provide agriculture for the colonies. Now you can eat popcorn and hamburgers with real bread rolls thanks to those. For thousands of years, the seeds were kept without human attention. This isn't a miracle, but an accurate scientific calculation. The vault is built underground at a depth of 390 feet. There are no earthquakes or floods there, and the permafrost provided the optimum temperature for the seeds to survive. Most metals are mined from ore. These ores don't contain pure metals, but only their chemical compounds. To get pure iron, the ore must be smelted first. But there's a problem. Metals from ore oxidize on contact with water or oxygen. Simply put, they rust. This is how metal returns to its natural ore state. That's why nails, metal fences, bridges, and houses rust and collapse. But this doesn't happen with gold, silver, and platinum. Things made from these metals are eternal and will never lose their shape. Of course, if you don't start hitting the rings and pennants with a hammer. During excavations, archaeologists find thousands of jewelry items. Earthlings love to wear them on their bodies. Crowns, luxurious necklaces, wedding rings. All this jewelry is now history, kept in galactic museums.
What is the fastest moving thing in the universe? That we know about, of course? It's light. Its speed in a vacuum reaches 186,000 miles per second. If people could travel at such insane speeds, we would have already explored hundreds of new worlds which are inaccessible to us today because of how far they are located. Interestingly, while traveling at the speed of light, you would experience time differently. Your mass would become infinite, and you would slow down. That's because the faster an object moves, the more mass it has. That's why, in real life, traveling at the speed of light in the conventional way doesn't seem possible. Okay, another question. Could we slow down the speed of light? In 2015, a team of scientists from Scotland claimed they had found a way to do just that. They sent protons through a special mask, altering their shape. And in this malformed state, super tiny particles of light started traveling way more slowly than regular protons. It's true that the difference in speed was almost imperceptible, but the fact they had managed to do it was amazing. It means that the speed limit of light isn't as unchangeable as we thought before. It's another question why anyone would want to slow down light, as if it's not slow enough as it is. Ah, I see. This last statement might sound confusing, but let me explain. We humans are used to traveling at unhurried speeds of 60, 70 miles per hour on the highway. So to us, the speed of light seems to be unreachable. But how about this? If we reduce the observable universe to the size of our planet, crossing the Milky Way galaxy would be like walking a few houses down the block to visit your friend. And still, it would take a whopping 100,000 years if you traveled at the speed limit of this Earth-sized universe. This example shows how incredibly slow it would be for a spaceship to explore other worlds at the speed of light. Crossing our home galaxy would span more than 100 human generations. And even if we let humans be and concentrate on protons dashing across the solar system, the speed of light would still turn out to be too sluggish. Astronomers have calculated that it takes light almost as much as 45 minutes to travel the distance between the Sun and Jupiter. And it takes light 5 hours to reach Pluto. When you look up at the sky at night, you see stars as they were a long, long time ago in the past, thousands of years. That's how long it takes the light they emit to reach us. So now that we know that the speed of light is indeed pretty slow, we can try to find the answer to the main question. Why is it so? So far, the only answer astronomers have is because. A tiny bit more satisfying version of this answer sounds like this. The universe is designed in such a way that protons move with such velocity. There's no specific reason why it should be this way, it's just the way it is. As you see, the answer is a non-answer at the same time, and we're simply stuck in this slow universe. But would it be better if light was much faster? What would our lives look like if the speed of light was boosted by a factor of 1,000? Then, a spaceship moving at the speed of light could cross the Milky Way in less than a century. A trip to Alpha Centauri, the closest star to Earth other than the Sun, where potentially habitable planets may dwell, would take less than 2 days. Computers and different networks would function way faster due to enhanced optical speeds. But at the same time, the Sun would also become much hotter, around 1 million times hotter. And it would mean only one thing. Earth would be boiled in no time. So we should probably be grateful for our slow speed of light. If it were even a bit faster, our planet wouldn't exist.
The speed of light is the fastest thing in our universe. It travels across space, passing through Mercury and Venus to reach us, and it's slowing down. No need to panic though. The Sun is getting weaker, but we won't see the effects of it for another billion years. In the vacuum of space, the speed of light is around 186,280 miles per second. Any slower than that, and humans would see the changes firsthand. There would be some awesome effects, like colors changing and the brightness of objects fading. We'd also notice some differences in everyday objects, their length and shape. Scientists created a simulation to see what would happen if the speed of light was slower. In a vacuum, the speed of light can't change, but if light passes through different materials and objects, it alters the way we perceive things. Light acts as a wave and a particle, meaning that it's a wavelength. The color and frequency are determined by the distance from crest to crest in the wave. It behaves similar to sound with the Doppler effect. Imagine you're standing in the middle of a busy highway and a honking car speeds through. Wow, that was loud. You can hear that whoosh-like sound of the horn because the moving object produces the sound while you're stationary. The frequency and pitch seem to change, but it's just the sound reaching your ear faster than it would if you and the car were both stationary. Light behaves similarly. The wavelengths change if the speed changes. Moving toward a light source and making the wavelength shorter will shift the color to a blue and violet hue. Moving away from the light source, and you'll get something more reddish. So if the speed of light slowed down to walking speed, we'd notice the colors changing when we approach an illuminated object. At the same time, the color would change around us and behind us. If you walk sideways, the colors you're walking toward would become bluer, and everything in the distance would become red. This information is useful to astronomers who are studying objects in space. If they're blue shifted, that means the object is moving towards us. And if it's red shifted, then it's going in the opposite direction. In fact, everything in the universe is red shifted, proving that the universe is expanding and getting further away from us. The slower it gets, the brighter it becomes. That's because the photons become more present for us to see. At this rate, we can see invisible light and increased intensity. You won't notice that effect much if you're standing still, but because of the Doppler effect, moving towards an object will have different colors and different light intensities. Another phenomenon we'd experience is time dilation. It's when you move at a similar speed as light and time decreases relative to someone who isn't. Space and time are relative. So if you're sitting at your desk wasting hours away, yeah, sounds familiar, doesn't it? All your movement will go through time and not through space. You're stationary, but you're still technically moving forward in time, slowly aging. The faster you move through space, the slower your movement through time will be. If you move at the same speed as light, then all your movement will be through space and not through time. To notice that, you'd need another person to watch you. You're not in a time machine. You're both on Earth, experiencing the same time flow. To you, experiencing this firsthand makes it feel like you're going faster, because you're getting a lot more movement in space in a given time. The closer you get to the speed of light, the smaller you become. Well, not really, but it depends on who's watching. If you're the one traveling at such a speed, an object nearby will seem small, just as someone who's watching you travel at the speed of light will think that you're smaller than you actually are. The simulation that the MIT scientists conducted showed that if the speed of light drops, everything will become stretched out like a pancake. If you see mountains in the distance and then run at the speed of light, they will appear further away. Objects will become distorted, and it will feel like you're getting to a certain place faster because time has slowed down for you. If you're standing completely still and someone standing on your left-hand side throws a cube-shaped object over to your right-hand side, then naturally, you'll see one side of it unless it flips around. But in this new reality, you'll get to see the front side wrapping around the visible side you're seeing. If you're moving at the same speed as light in an infinite space, everything will be stretched out as you reach infinite speeds. In a world where people can walk at the same speed as light, we'll perceive nothing as normal. We'll have to get used to the way we see objects. Every movement we make will result in drastic shifts of colors. Even turning your head to look at something will feel weird. Let's say you're in a supermarket buying groceries, and you walk from aisle to aisle. The milk at the end of the counter will look like it's really close to you. But when you approach it, you'll start to feel like it's getting further away from you. The milk will also look a bit red. As soon as you get closer to it, it will shift to blue. If someone is passing through with a shopping cart, you'll see it as a sort of 3D model of a shopping cart. The color will shift as it gets further away from you. It will appear far away, but it's right in front of you. In fact, we don't really know the actual speed of light. Physicists gave it roughly 186,280 miles per second, but that constant is just for them to calculate other scientific stuff so we can understand it better. The problem is that we can only measure light with light beams and mirrors, but it's not like all we have to do is point a light beam at a mirror and measure its original path and its reflected path. Einstein's theory of relativity states that the original path of light moving from the source to the mirror may not be the same speed as the reflected light from the mirror back to the source. Hypothetically, if it takes light 10 seconds to travel from the source to the mirror and then back to the source, then we can conclude that each trip takes 5 seconds. But Einstein's theory is that it could take 9 seconds for light to travel from the source to the mirror and only 1 second from the mirror back to the source, or vice versa, or maybe completely different numbers altogether. That's why it's so difficult to measure light. A breakthrough came out for scientists when they managed to slow down the speed of light to 0 without losing its brightness. They did this by using ultra-cold atom clouds made with photonic crystals. These crystals are materials punctured with billions of tiny holes where light can refract. But what if we lived in a world where light stopped halfway? You'd wake up one morning and feel like it's twilight. You'd open the curtains and see that many car lights are on, but aren't so bright. You turn on the lights in your room, but feel like the bulb is tapping out. You replace it with another one, but it doesn't do the trick. You turn on the lights everywhere in your house, but it's all just giving weak light. You're confused and try to check if there's a problem with the electricity in your house, but it seems to be working well. You check on your neighbors, and they also have the same problems. Even experts in the field can't understand what's going on. Hours pass, and it's all the same. All the light in the world seems to have frozen halfway. Your phone is low on brightness, even though you bumped it up to maximum. Everything is getting darker. You learn from the news that it's a global problem. Light is slowly diminishing, and soon there won't be any of it in the world. You decide to wait it out while everyone else is panicking.
Whoa, something doesn't feel right. Everything seems shaky. It's definitely not an earthquake, and it's actually getting worse. The clouds seem to move quicker than usual, and the animals are going into a frenzy. The news anchor pops up on the TV in an alarmed tone and says, "Good morning. We're sorry to interrupt your program. Scientists have just discovered that the Earth's rotation has been fluctuating at an unusual rate. A group of specialists believe that the Earth is increasing its rotation with every second, and they don't know why. Even if the Earth increased its speed by 1 mile per hour, the day would only get shorter by a minute and a half or so. We wouldn't really feel it, and you could go on like nothing is happening. But as the Earth spins faster, our bodies, which are adjusted to a 24-hour timing, will have a hard time trying to cope with it. If you live by the equator, that means the rotation of the Earth is going quicker than at the North and South Pole. The area by the equator needs more time in order to complete its full rotation from the starting point. You'll experience more rain than usual. The Earth's rotation keeps the weather consistent and balanced so that nothing abnormal happens. But because the Earth is moving so fast, the weather is acting up. We'll start to see more storms and more cozy days inside, sipping on hot cocoa. Even though it seems weird, everyone can go about their day. But if the Earth picked up some speed and moved at 150 feet per second, the day would be reduced to only 22 hours. It kind of makes you feel jet-lagged 24/7. Every business works with the 24 hours a day schedule, so taking away even 2 hours can have catastrophic effects on the world economy. The whole calendar will have to change and adjust to the new timing. Clock designs will change with the new midnight, replaced with 10 o'clock. And with each week, the hours will shorten, so there will be no proper way of telling time except by sunsets and sunrises. The weather will continue to get worse and worse, feeling like the rain will never stop. The animals that rely on weather patterns won't know how to function, and mass migrations will occur from almost all species of animals. Flocks of birds will be flying everywhere and reach places they normally won't go to, affecting the whole food chain and ecology. Woods, jungles, and other places where animals roam are kept in proper balance when unaffected by humans. If it constantly rains in certain areas, then floods will force animals to move to other territories and compete with the predators in the area. If the Earth picked up speed every day, then standing on a scale in the Arctic would tell you weigh 180 pounds. But around the equator, you might weigh about 179 pounds. That's because of the extra force opposing gravity in that area. With the Earth spinning faster, all airlines around the world stop, since the radar systems have gone haywire and the weather is too dangerous to fly. Everyone has to get around by car. Satellites are positioned in such a way that it's crucial they remain where they are in order to bounce signals to us. Because of what's happening, Wi-Fi and TV signals can't go through. Communications around the world will end up short and slow, and eventually we'll have a total communication blackout. Ships will cease to operate and global trading will collapse, adding extra damage to the already failing world economy. Winds will get stronger and faster than usual, which means temperatures will change. Storms like hurricanes will be stronger than ever and have more energy for destruction. And still, at 100 miles per hour, the equator will now be swallowed up in the water. The Amazon basin and small islands will now completely submerge in water by around 50 feet. Most of the plant life will be in danger, especially by the equator. With woods threatened by floods, more animal environments will be in jeopardy. The trees and plants won't survive so much flooding. If the Earth rotated so fast that the hours would now be reduced to 15, then we'd probably feel like we're always on a jet plane going through turbulence. It would be impossible to sleep if the Earth kept picking up speed every second of the day. So days would be around 7 hours long as well as nights. The whole world would be flooded, except for the highest points and the tallest mountains. If that happens, humans will most likely end up there clinging to the last remaining clear patches of land. Most of the animal life will be extinct as well. And as the Earth is spinning faster and faster, the crust will lose its durability, allowing more frequent and stronger earthquakes to happen. Volcanoes will erupt all over, even if they're submerged in water. It'll go on like this for quite a while. Many major natural disasters like earthquakes, tsunamis, volcanoes, and even melting ice sheets have sped up the speed of the Earth by milliseconds. So, with the Earth's continuing speed increasing, these natural disasters will make the planet go even faster. Even if it's just for milliseconds, it's enough to have major consequences. The Earth is now spinning at 1,000 miles per hour, and as you're sitting with the rest of the survivors, you feel yourself levitating slightly. You'll see tiny pebbles and rocks floating inches from the ground. The clouds above you are passing like shooting stars. The air is thick with moisture, since water is rising to the top, forming thick clouds ready to pour. But since gravity is weaker, some of the rain is suspended in the air. Many small objects will be floating around as if you were in space. The days and nights won't be longer than a few hours. At this point, the whole world will be flooded, and the crust will be 80% gone. If it goes on any longer, there won't be any living things around, probably except for microscopic creatures that can withstand extreme and harsh conditions. The Earth would need to spin at approximately 17,600 miles per hour to cancel out the gravity for things to start floating around. At this point, all the water in the ocean will rise and look like reverse rain. The large mountain rocks will separate from the bedrock and levitate above the ground, looking like little planets in space. The Earth is now spinning 17 times faster than usual, which makes one full rotation around its axis only 84 minutes instead of 24 hours. If you manage to stay that long, then you'll literally see the days and nights go by in an instant. You'll also be floating aimlessly in the sky, bumping into rocks and other surfaces. You won't recognize anything anymore. The Earth's crust is ripping apart, exposing the magma underneath. So landing on the ground isn't an option. You'll see outer space as you go higher and higher. You won't know how fast you're going, but all you know is that you're probably the only human left in this spinning world. The Earth will eventually spin so fast that the rest of the layers will start to peel off, exposing the Earth's interior. It'll start to squeeze itself from the core until it becomes similar to a pancake. Nothing can survive at this point. So much heat will be produced from the core that the planet will heat up like a microwave. All the water will disappear, and it'll look like a red dot in the solar system. And once it starts to approach the speed of light, time will freeze. The rocks and floating elements won't move and will eventually be distorted. And with enough effort, the Earth will eventually turn into a black hole. Of course, nothing like this will ever happen. According to scientists, Earth will most likely slow down in rotation. Ever since the Moon came into the picture, the Earth has been slowing down by around 4 miles per hour every 10 million years or so. That's because of the Moon's gravitational pull on our little blue planet. It'll most likely go on that way. So hey, what's your hurry? Whoa, the light from outside your window just got brighter. It's 9:30 in the evening, and you have a huge exam coming up tomorrow. You peek outside to see if your neighbors use their floodlights again. But they're outside looking up in the sky. You stick your head out and notice that the moon got a lot bigger, double in size. You run outside and ask people what's going on. But they don't have a clue either. You take a picture of it and post it on social media. You view your feed and see that everyone is talking about it. The dark sky is brighter because the moon has more real estate to reflect light from the sun, making the light more intense. You can feel a slight imbalance while walking. Every time you take a step, it feels like you're walking lighter than usual. Because the moon became so large, its gravitational pull became stronger, so gravity became weaker. Suddenly, you look below you and feel your socks are wet. You run and hop on the top of a car and see that there's water flooding your neighborhood. Everyone tries to find higher ground or run back to their houses. This isn't a fire hydrant that busted and is spewing out water. This is ocean water seeping in. You're confused and lose your balance. You slip and fall in the water as it rises. Some people are in their cars, but they can't drive anywhere because of the water. You live near the ocean, but there has never been a tsunami or any flood reports in your whole life. There are no reported earthquakes around the area, so something strange is happening. You run back to your house, trying to see if you can get out your old inflatable raft to help you with the flood. The only problem is that you need to inflate it but don't have your pump. You inflate it with your mouth at first, but it'll take forever to pump it up. You search around your house for an alternative and find your hairdryer. You plug it in and inflate the raft as much as you can until you use your mouth to do the rest. The water level rises by every second and has now entered your house. You pack up a bag with a good flashlight, some food, and thermal blankets. You go downstairs and see that the water is now at your knees. You keep walking until you reach the door. When you step outside, the water pushes you left and right since the waves are very harsh. Since gravity has changed, it's not easy to swim around. You get your raft ready and use it to float yourself down the current in your street. It doesn't help that the water is freezing, and you're in the middle of February. After a while, you reach the highway where water is coming directly from the beach. You manage to get on a high surface and take out your phone. You kept it in a protective compartment in your bag for safety. You only have 15% battery left, but you brought your power bank. You call your family to see what's going on, but they too have no idea. You venture into the forest and try to spot an old cabin you used to visit as a child to see if you left your old bicycle there. After a few minutes, you find it and bike across the mountain to escape the flood. You can't seem to balance yourself since the gravity is affecting you. Some scientists sit around with laptops and spreadsheets, attempting to understand what's happening. Everyone is shouting and throwing out random solutions, but nothing seems to make sense. After a while, the head of NASA decides to launch an unmanned rocket to the moon. The rocket is ready in a few hours, and everyone is awaiting orders. 3, 2, 1, blast off. The rocket soars in the air and approaches the moon. It exits the Earth's atmosphere and travels at full speed in that direction. After a day or two, everyone gets live footage of the giant moon. According to the studies, the rocket can't be too close to the moon since it may have a stronger gravitational pull. However, the footage shows that tiny particles are floating around it, similar to Saturn's rings. These rings look like a giant disk surrounding the large planet, but up close, they're just particles that are the size of rice grains to the extent of a large bus. They're orbiting Saturn because of the gravitational pull. The images show that these particles are big and small, which doesn't make it safe for the rocket to get any closer. So it suspends itself nearby to orbit the moon and unleashes a mini-rocket that looks like a drone to get closer. The particles are many miles thick, making it difficult for the mini-rocket to maneuver. It flies closer and the particles start crashing on it. It's a good thing that the mini-rocket is durable for this. The rocket finally gets past the particles and lands on the moon. Gravity has gotten stronger since it inflated in size, which almost broke the rocket. As soon as it lands, another robot pulls out and starts driving around the surface, trying to get some clues. As of now, nothing is happening. But they're noticing some quivers coming from deep inside the moon. The moon's core is reacting abnormally. It looks like it's getting bigger and bigger. Scientists don't know if it will stop growing at a certain point, so the only way to find out is to drill a hole deep inside to uncover the reason. You're pedaling away and reach the other side of the mountain. The ground is shaking, and your balance is getting worse. You look across the mountain and see that the whole other side of town is flooded. You get your raft and supplies and make it there. You find a rowboat and paddle as fast as you can until you reach the lighthouse. From there, you can try to find the NASA station. Suddenly, you see a large rocket erupt from the ground and into the sky. You know for a fact that your brother is there working, but cellular networks are down. You paddle your way there for safety. The little rocket that landed unleashes a small drill strong enough to go miles to the center. It'll take days for it to reach down. So NASA is already launching another rocket to fly off and bring a bigger drill. The only problem is that the moon is getting bigger, so the particles around the moon also gather a lot more. The moon is reaching the Earth's size, getting bigger by the minute. The flood could reach several coastal states, and many micro-islands could be submerged, so it needs to be prevented. Gravity could affect the structure of most of the buildings, causing them to collapse one by one. But the little robot will not let that happen, so he's drilling to figure out what's going on with the moon. Some of the rocks appear to be getting hotter as it digs. This could be a sign of the moon expanding, which might ultimately explode. The scientists in the room are baffled and don't know what to do. The lead scientist, who is your brother, calls you, but he can't reach you. Meanwhile, you're still paddling around, trying to get to NASA. On your way, you head back to the mountains to stay on dry land. When you arrive back at the old cabin, you see some strange men wearing trench coats looking for you. There's a stare-off until they chase you. They seem odd, like they're not from Earth. The drill has reached its maximum depth and can't go down any longer. Also, the control transmission is getting weaker. Suddenly, a figure pops out of nowhere and flashes its lights on the robot. The transmission chops and only show little snippets of the giant figure eyeing the robot. A little creature descends from the figure and walks toward the robot. Everyone at NASA is freaking out and recording every single frame. No one can believe what's going on. After a while, the creature transmits a signal that NASA can't decipher. But the creature seems friendly. The creature gets back into its ship and in an instant disappears into thin air as it teleports away. The moon starts shrinking. It's getting back to its normal size. Everyone celebrates in NASA and around the world. The currents become calmer and retreat to the coast. It's a good thing everyone reached the higher hills before.
The large ball of fire thousands of miles away from us is the brightest object in our solar system, as well as the biggest. If Jupiter was the size of a basketball, then the Earth would look like a tiny little grape. But the Sun makes even Jupiter look like a joke. That big burning ball in the sky is made up of hydrogen and helium, and is 864,000 miles in diameter, making it more than 100 times wider than our little blue planet. It's 10,000 degrees Fahrenheit just on the surface, and 27 million degrees at the core. The Moon, on the other hand, is a little easier to grasp at around 2,160 miles in diameter, which is only less than a third of Earth. It might seem pretty big floating in the sky, but that's because it's the closest object to us. But what if the tables, or in this case, celestial bodies, have turned, and the Moon suddenly became brighter than the Sun? Let's explore several scenarios. Scenario 1. If the Moon becomes brighter than the Sun, The nights will be brighter than days. It means your sleep cycle will be disrupted. All nocturnal animals will be utterly confused. When is it time to go out and eat now? In the extreme north and south poles, the nights and days are for months on end. So people living in the area already have an idea of what it's like to sleep at 11 p.m. with the sun shining brightly above them. For the rest of us, it won't be easy. Let's say you're out camping and prepare an awesome meal and gear up for the dark nights. As you trek into the forest, you find a spot that has an awesome view of the lake and the clear sky above. It's 7 p.m. and you start a fire for some s'mores and get the telescope ready. The only problem is that when the sun begins to set, the moon lights up the sky even brighter. It's surprisingly not as hot as you'd imagine, since it's not direct sunlight, but regardless, it's still pretty hot. Scenario 2. Temperatures will surely rise either way. That means snow will melt away faster than you can go, What's going on? The snow on the mountains will be the first to melt, followed by the polar caps. With so much heat, the sea levels will rise and take small remote islands scattered across the ocean underwater. Coastal towns will go down and everyone will live closer inward. This will likely cause a chain reaction in the world economy. There will be no more winters, which means no more winter activities like skiing, snowboarding, or snow fights. Animals and plants all around the world will be affected. The world will turn into a large desert. Water will get scarce over the years, but people will find a way to preserve it. Scenario 3. You're sitting behind your desk, bored. You're losing business. People aren't buying as many sunglasses as you thought. But when the moon suddenly becomes brighter than the sun, and everyone needs to wear those glasses 24/7 when heading outside, you can't keep up with the demand for sunglasses, so you hire more people and grow your business. You eventually become the best sunglasses business in the country. They don't recommend looking up at the sky at any point of the day or night. Cities are covered with large visors to reduce the brightness every day. Sunglasses will come in different sizes and shapes for different times of the day. Some will be like goggles strapped around your head, while others will be like large helmets. Scenario 4. The moon's atmosphere is so thin that it can't contain anything in it. Just like over deserts on Earth, there are no clouds to bring some rain, which is why it's always hot or cold. Yeah, the biggest desert in the world is the whole continent of Antarctica, which is a cold, barren desert, contrary to what people think of the Sahara Desert. So if you still want to land on the moon, you better think twice now. People who are working at the International Space Station will have to find a new office. The moon will be too bright to bear, considering how close they are. If the moon is just brighter than the sun without the heat part, then the space station will only require adjustments to keep the light out. The reason why we see the moon in various shapes is because of its position in relation to the sun. The moon doesn't rotate, unlike Earth. It's kinda glued to us and is always showing the same side. So, depending on the moon's position during the month, we'll have a super bright night during the full moon, and relatively shiny nights during the rest of the month. Scenario 5. If the moon became brighter than the sun, it would produce more heat than the sun and probably become larger. Gravity on Earth would change significantly because of the moon's new size. The whole orbit structure would change and affect the celestial objects floating in space. Planets would soon begin to orbit around the moon. Earth might move further away from the sun. If that happened, then everything would have to readjust to the radical changes in gravity. Weak gravity means buildings wouldn't have a solid foundation to sit on and would eventually collapse. Bridges and large monuments would also fail to hold up. People wouldn't be able to walk properly and would do it in a funny way. Scenario 6. In many of these scenarios, I mentioned how the moon would be brighter than the object emitting light, but in this case, the sun would have to come from the moon, reflecting from the sun, which means that the sun would have to be twice as bright as it is now. If the sun got 100 times bigger, it would shoot out more rays, which can be damaging and throw off a lot of radiation, harmful to every living thing on Earth. The gravitational pull of the sun might attract more planets to orbit around it and cause other objects in space to join the orbit. The planets would be partying in our galaxy club, and we might be thrown off our orbit course. Of course, this would pose a bigger risk to everything on Earth as things would get hotter and drier than before. Scenario 7. If we're talking about the moon getting brighter, we can also assume it would get closer to Earth than it is now. The brightness won't be the problem here, as gravity will cause major changes on Earth. But every day, 24/7 will be high tide. It will be so extreme that there will be constant floods in every coastal town. All islands will be submerged, which will increase the population of inland cities. Marine life will be having the time of its life when water overtakes the land. Boats will have to be re-engineered for new conditions as well as submarines. Air travel will be the priority, but large cruise ships will look futuristic and have an extra build to sustain the harsh waves. Nighttime will be pretty bright on regular days. It will raise the global temperature, which will melt down the snow, causing the sea levels to increase even more. Comets and other celestial objects will be drawn to a closer gravitational pull, so we will always have to look up whenever we go outside. But no worries, the moon is still up there as it is for a very long time. The Earth and the moon's relationship is complicated. Luckily, we only have one natural satellite. Other planets in our solar system have multiple moons revolving around them. Some are so huge that they're the size of Earth. Imagine several of those affecting our home. But that's a topic for a completely different story. When you see it in the sky, it looks round, but the moon is more of an oval shape, similar to a lemon. This shape, flattened with a bulge on each side, came out billions of years ago when extremely hot tidal forces shaped its crust. They heated up some regions more than others. Gravity from our planet has helped to exaggerate this lemon shape over time. When they were getting ready to send missions to the moon, some researchers were worried because there was a thick layer of dust on the lunar surface. They were afraid seas of dust were both soft and thick enough to swallow their lunar lander. But even though the surface there is dusty, this layer is just too thin to cause complications. Our moon certainly isn't the biggest one in the solar system. The champion here is Ganymede, one of the 79 moons circling around Jupiter. But our moon is the largest in relation to its parent planet. It has a diameter of more than 2,000 miles, which is slightly bigger than the quarter of the size of the Earth. Pluto, for instance, has a smaller moon-to-planet ratio. Its biggest moon, Charon, is almost the size of Pluto, which is why it looks like a double dwarf planet system. How long would a walk around the moon take you? When the Apollo astronauts were there, they managed a walking speed of approximately 1.3 miles per hour. On average, you walk twice as fast down on Earth. The low gravitational force on the moon would give you significantly less traction on the ground. But those special spacesuits astronauts were wearing were never actually designed for long-distance hikes. In theory, you could maybe reach the speed of 3 miles per hour before you'd need to break into a run. At this pace, you travel 6,770 miles, which means making a circle around the moon in 91 days if you're walking non-stop. Why does the moon change its shape? It goes through different phases each month, starting from the new moon and gradually going to the full moon, just to do the same thing all over again, but in reverse. The sunlight hits one half of the moon at a time. This gives it a night and a day side, just like we have it here on Earth. The shape we see the moon in depends on where it's located compared to the sun. If it's directly between us and the sunlight only hits the side we don't see. That's a new moon. It appears completely dark in that phase. But when it comes to the far side of our planet from the sun, its day side completely faces the Earth. That's when we see a full moon. After the initial phase, when the moon is new, we'll see more of its surface in the sky as it orbits our planet. It's something we call waxing. The moon in this phase first becomes a crescent. The first quarter moon is when it's half full. After that, it goes into a gibbous moon phase, when it's larger than half full, but not yet full. After it reaches the full moon phase, it slowly shrinks and goes through the same phases but in the opposite direction. While up on the moon, you'd probably see human footprints there. True, no one has stepped there since the last Apollo mission in 1972. And the footsteps may stay there for many years because there's no geological activities on the moon, like earthquakes or volcanoes. There are no winds, rain, or other things that could erase these footprints. How would you get to the moon? Rockets are probably the first thing that comes to your mind, but a lunar elevator could be an even better solution because traveling in a rocket would be a difficult, expensive, and pretty dangerous way to try to reach the lunar surface. Why would people want to go there? It's not just about craters, an amazing view of our home planet, or other unique things the moon offers. It's also full of resources like a rare form of helium. Humans could use it in fusion power stations on Earth. We could extract some other rare elements too, and use them for smartphones and other gadgets. For a lunar elevator, we'd need to stretch a cable anchored to the moon's surface for 250,000 miles towards the Earth. We wouldn't be able to attach it directly to our planet because both Earth and the moon are moving. But we could terminate high in our planet's orbit. We'd have solar-powered robotic shuttles that would move up and down the cable. This is like having a conveyor belt to ferry rare and precious resources our way. The cable would be as thick as a pencil and would weigh 40 tons. It sounds expensive, but a lunar elevator would most likely pay for itself within only 53 trips. The moon is in constant motion. It rotates on its axis and circles around the Earth, and it makes the same amount of time for the moon to make a circle around the Earth and rotate once on its axis, compared to our planet, which rotates on its axis every 24 hours, and makes a full circle around the sun in 365 days. So, the moon is tidally locked to our planet, which is why we always see the same side of the moon. One theory says the moon probably formed when a large Mars-sized object from our solar system hit the Earth. They collided 4.5 billion years ago when the solar system was still in its early stage, which was pretty chaotic. If this theory is correct, around 60% of the moon is made of lighter elements that are also present in the outer layer of our planet. A lucky set of circumstances lets us see total solar eclipses from our planet. The moon is the perfect size and distance from the Earth to appear the same size as the sun when we're looking at it in the sky. When the moon passes between the sun and us, it covers the sun perfectly. Plus, you can see an impressive halo that illuminates its edges. If it were any farther from us or smaller, a solar eclipse would only look like there's a blot on the sun. Our moon contains the water that kinda jumps around. There's water there locked up in ice. Some water molecules move around the surface as the moon cools and warms during the day. The water gets stuck on its surface until the lunar midday, when the sun is above the upper branch of any of the moon's meridians. At this point, some of the water melts, heats up, and ends up in the delicate lunar atmosphere. Its atmosphere generally contains some unusual gases, including potassium and sodium. Venus, Mars, and Earth don't have these in their atmospheres, so the water stays and floats there until it gets to a cooler area. Then it settles back to the surface. There's a specific anomaly under the surface of the south pole of the moon, a giant and extremely dense blob of metal lodged in the mantle. And, most likely, it's altering the moon's gravitational field. No one knows how such a huge blob of metal ended up trapped under the lunar surface. It could perhaps be remnants of the iron-nickel asteroid. 4 billion years ago, this asteroid crashed into the far side of the lunar surface and created this enormous South Pole Aitken crater. Our natural satellite is shrinking. Its interior is cooling, which results in the moon getting over 150 feet skinnier just as a grape wrinkles as it's shrinking down. But a grape has flexible skin and the lunar surface crust is brittle. That's why it breaks as the moon is getting smaller. That way, it forms thrust faults. One section of crust pushes over the closest part. This has been going on for the past few 100 million years. These lunar faults are still active. They probably produce moonquakes as the moon gradually shrinks and cools all the time. Some of these quakes are strong, maybe 5 on the Richter scale. During their orbit around the moon, astronauts took images of Ina, a quite unusual volcanic deposit. Ina is not that old. It might have been formed somewhere between 3.5 and 1 billion years ago. The volcanoes on the moon were probably active during the age of dinosaurs. If only they could have invented telescopes. They'd probably have a magnificent view of lava oozing from the lunar surface from time to time. The moon has its own time zone called Lunar Standard Time. It doesn't correspond with the time on our planet. A year on the moon lasts 12 days. Each day is about as long as a month on Earth. These days got their names after astronauts who walked on the moon. The days are divided into 30 cycles. The cycles are divided into hours, minutes, and seconds. The calendar started when Neil Armstrong set his foot on the moon on July 21st, 1969.